Welcome to Reasons to Believe, the television episode where we explore new reasons, new evidences to believe in Jesus Christ as Creator, Savior, and Lord, and for the accuracy and the reliability of the words of the Bible, not just for faith and practice, but in all disciplines, including science and history. We're in the middle of a series on the anthropic principle, the concept that the universe has been fine-tuned or designed to provide a home for the human species. And I've been joined by two of our astronomers, Dr. David Rogstad and Dr. Jeff Zwierink. And if you've missed the last two episodes, they are archived on our website at reasons.org, and you can go there for resources on the anthropic principle. But you got a letter you wanted to read to.
Yes, I would like to. These are always very encouraging. Actually, this is an email from Harry. It says, "This is to thank TBN for televising Hugh Ross's Reasons to Believe. This is the best program for believers as well as non-believers to learn about the miracles of creation and God's design for human life on the earth. It teaches the Bible is scientifically reliable, a source for believing in God, and challenges the evolutionary theory and other religious beliefs." And then, as I said, this is from Harry. So it's a very encouraging little note from Harry that tells us that this is an effective program.
Well, we're trying something a little different in this program. This is the first series we've done where we've pulled together scholars that are all within the same discipline. All three of us are astronomers. And we really appreciate hearing some feedback. Is this working for you? Any suggestions you might have, critiques, things that you do like. So please let us know what you think, and let Jen and Paul know as well. Well, we left off last time talking about what we call the gross features of the universe.
The fine-tuning of those
which
features.
means the universe as a whole.
Yes.
And how there are 48 different characteristics that we see in these gross features that must be fine-tuned to allow life to be possible. And we should probably lay our cards on the table. We're not talking about just life as we know it, but any conceivable physical life requires the fine-tuning of different cosmic parameters. And the two we discussed last time was the mass density, which must be tuned to within 1 part in 10 to the 60th for life to be possible, and then the space energy density, or the cosmological constant, which must be fine-tuned to within 1 part in 10 to the 120th.
Absolutely.
Well,
phenomenal.
By comparison, the best we humans can achieve by way of design is 1 part in 10 to the 23. But as we mentioned, there are 46 other characteristics that astronomers now see in the universe.
And one thing it's kind of been interesting to me is I know other people have put out the list of 100 things or whatever, but my experience with having looked at this over the course of the last 10 or 15 years and what you've written and such is that it used to be 13 and it used to be 20. The list is growing throughout time. Some of them we may find a good explanation as to why they're not designed, but the list in general is growing and getting larger as we study more and more.
Well, this is one of the ways you can put the cosmic creation model to the test. I mean, if the atheists and the agnostics are right about the universe, as evidence for design should decline with time, and we'll find natural explanations for what we thought was supernatural fine-tuning. But if we're right and they're wrong, the more we learn about the universe, the more we should see this evidence for supernatural design accumulate. And I like what you said, Jeff, is that because we're human, we may overinterpret or underinterpret. We may see design where design actually isn't there, and we may misdesign where design isn't there. But what counts is the overall trend. Ignoring our human mistakes. As we learn more and more, what is the trend line? Is the evidence for supernatural design accumulating or is it declining? And basically we're telling the story that for the past 40, 50 years, it's been increasing and increasing at an exponential rate.
And there's been at the same time a lot of effort gone into trying and to explain these apparent design parameters, to try and come up with naturalistic explanations for them. And that has increase the number of explanations, but all of them have failed up until now.
Well, ironically, all these attempts by non-theists to explain away this design has wound up producing more evidence for design. That's
Yes.
something we'll get into.
We'll get into, yeah.
But let me take this back historically. I mean, the first physicist or astronomer to really discover that the gross features of the universe must be fine-tuned, well, some say it's Paul Dirac, but he was really looking at the mathematics that had to be fine-tuned. That certainly is significant that, the math of the universe isn't an accident. There are certain laws that must be in place for any of this design even to be possible. But it was Robert Dicke at Princeton University in 1961 that published the first paper where he said the features of the universe itself must be designed beyond the math. And he was really speaking about the gravity and the electromagnetism. These are two of the fundamental forces of physics.
Now, there are four forces, as we have in the
Right.
visual right now.
Yeah, there's electromagnetism, which really determines whether or not you get molecules. There's gravity, and that determines whether or not you're going to get stable burning stars as it interacts with electromagnetism. You got the strong nuclear force, which determines the degree to which protons and neutrons stick together in the
Holding
nucleus.
one another in the nucleus of an
Right.
atom.
Then the weak nuclear force is the force that governs radioactivity.
How large nuclei
Right.
will break apart
Well,
and produce radioactive.
all four must be fine-tuned or very carefully designed in order for light to be possible. I mean, for example, with the strong nuclear force, if you make that force a little bit weaker, then none of the protons and neutrons stick together, and you wind up with a universe that has only hydrogen.
That
in it.
only has the smallest atoms in
Right.
size. That's right.
But if you make that force too strong, then all you get, protons and neutrons will stick together so effectively that all you have is heavy nuclei, the kind of stuff that you're studying in your research. And then you're going to have a universe that both ways, it's missing out on carbon, oxygen, and nitrogen, and life will be impossible.
Well, and what's true too is not only do they have to be fine-tuned for things where they're only, but you have to have electromagnetism the same strength relative to gravity, and the ratios of them are also important. And those have changed quite drastically over the course of the universe too.
Sure.
So.
Well, this is something that Robert Dicke pointed out, is that having a stable burning star isn't actually that easy. What you've got is the forces of electromagnetism that are working to expand the star, and the forces of gravity are working to contract the star.
Right.
And to have a stable burning star, those two effects must be in balance.
Balanced.
And he was the one that determined that you have to fine-tune the ratio of the electromagnetic force relative to the gravitational force to within 1 part in 10 to the 40th. That's 1 part in 10,000 trillion.
Absolutely phenomenal.
So,
Now, the scripture has some things to say about these laws of physics, does it not?
it really does. I mean, you got Jeremiah 33:25 making the point that God set up the physics, the laws of physics, so that they'd be fixed. Here's the verse. Have I not established my covenant with day and night and the fixed laws of heaven and earth? So this is one of the places where the Bible makes a statement that when God created the universe, he set up these laws of physics, and these laws of physics indeed remain constant until God conquers the problem of evil sometime in the future. Then you've got Romans 8, 18 to 20, which makes the point that this law of decay is something that God subjects upon the entire universe. The creation waits in eager expectation for the sons of God to be revealed, for the creation was subjected to frustration, not by its own choice, but by the will of the one who subjected it, in hope that the creation itself will be liberated from its bondage to decay and brought into the glorious freedom of the children of God. The whole point, I think, when it talks about this bondage to decay, it's referring to the second law of thermodynamics, what we call the Murphy's Law, that things tend to degrade over time. And
If
this
it
is a
can go
natural-
wrong, it will.
Exactly. It's a natural feature of the universe that things proceed towards decay at an increasing rate.
And I mean, most people that I've talked to originally, I thought that was something more talking about what God did at the fall of
Something
man,
bad.
and that's
A
not what you're
curse.
saying, though.
Yeah.
No. Well, I mean, these four laws of physics, gravity, electromagnetism, the weak and strong nuclear force, are all intimately tied into the second law of thermodynamics. I mean, you disturb any one of those laws and you're not going to get the second law of thermodynamics. Or put it the other way around, you disturb the second law of thermodynamics, it's going to have consequences on these other four laws.
In a sense, isn't the second law of thermodynamics a statistical expression of the relationship between these other forces?
Right.
And how those forces behave in the mass, as it were, in the large numbers that you find in molecules and atoms. And
Well, back to what Jeff said, because this is a common misinterpretation by many believers of Romans 8, but the passage itself says the entire creation has been subjected to this law of decay or bondage to decay. And when you're talking about the entire universe, that means this entire space-time realm. So it really is a statement right back to the beginning of the universe itself.
now all of these laws of physics, of course, come into play in how the universe evolves, changes with time. It starts out as this Big Bang. It expands in the early phases of the universe. Matter in the form of hydrogen and helium is formed. And then that matter begins to, under the law of gravity, to collapse, to form
Well, for
the
example,
objects that
Dave,
we see in the universe.
this matter of entropy or decay, if the universe decays too quickly, then you wind up with a universe that is only diffuse gas for its
It
entire existence.
doesn't collapse into stars and
It
galaxies.
won't make stars and galaxies.
Right.
But if the decay law is not as efficient as what we observe, then what you have is all the bits and pieces of matter going into black holes and neutron stars. So for life to be possible, the universe must be governed by a law of decay of a very carefully fine-tuned efficiency. It indeed must be extremely efficient. The universe must be extremely entropic or extremely driven towards increasing decay. Otherwise, you don't get stars, you don't get planets, you don't get moons.
Now, all of those things are fine-tuned as well. I think
Right.
we have some plan here to discuss galaxies and stars and types of galaxies.
Yeah, I'd like to segue at this point from what I would call the gross features of the universe. And again, we've only hit on a few. I mean, there's things like the uniformity of the universe, the homogeneity of the universe. Our books list 48 different characteristics of the features of the universe that must be fine-tuned
Right, and the
for
laws of
life to be
physics.
possible. But when you move from that to looking at the components of the universe, rather than 48 characteristics, there's actually hundreds of characteristics where we see this feature of design. And really kind of the plan we have for the next few episodes is to start with the bigger structures of the universe, then gradually work to things like stars and planets. But let's just examine, clusters of galaxies and galaxies themselves, and why we see design even at that
level.
large of a structure.
If I recall, we have sort of three characteristics, three levels, you might say, of design here. One is the clusters of galaxies. The second is the type of galaxies themselves within clusters. And then there's the internal structure of galaxies
Right.
that must be fine-tuned or must be just right.
Right.
And we can now kind of go through each one of these.
Right. Well, in terms of clusters, I mean, many non-astronomers may not be aware that the vast majority of galaxies are located in these giant clusters, and most of them are very dense clusters. And we've got some examples
Some
here.
really pretty pictures here. I've always loved these pictures.
Well, when you look at these pictures and you see these points of light, very few of those points of light are stars in our galaxy. What you're really looking at are distant galaxies. So even those little tiny points of light are themselves galaxies. And any deep image of the universe predominantly shows galaxies.
Galaxies and clusters. I remember
Right.
back when I was doing some research at Caltech here 30 some years ago, I was using a catalog of galaxies, of clusters of galaxies, and these were only what are called the rich clusters, the ones that have, several thousand to tens of thousands of galaxies in them, and there were in that catalog, which was just kind of a beginning catalog of these clusters. I think there was 2,700 clusters that were cataloged, each that had more than 1,000
Right.
galaxies in each one.
And those are the nearby ones.
And those are the nearby ones, the
Right.
ones that just the beginning of this
Right.
research into clusters of
Well,
galaxies.
what kind of cluster does our galaxy reside in?
Well, that's one of the key things here is what if we were in a cluster that was like one of these rich clusters? Would we be able to survive? Or is there a just right cluster? And that's a question, of course, that has been examined, and
Right.
and we have some overheads that talk about what happens if they're too dense, for instance.
Right. Well,
And-
if
Go
the
ahead.
clusters are too dense, and I think one way that we can do it is this way, is that stars are typically far apart, like the stars in our galaxy. Here's a couple of stars, and we're going to model them. The stars are typically 1,000,000 miles in diameter. But we model them down to this size. The average separation of the stars would be like putting this star here in Southern California, the next one in Siberia or Peru. The stars are very far apart,
Right.
and so our galaxy is essentially empty space. But if I were to use these as model galaxies, where this would be galaxy A and galaxy B, the average separation of galaxies in the universe would be kind of like this. Galaxies are close together. And most galaxies are found in these dense clusters of galaxies. Well, the fact that they're so close together, even 14 billion years after the creation event, means that these galaxies interact with one another. And it's their interactions that disturb the orbits of stars around the centers of these galaxies. And so if you've got big galaxies or too many small galaxies in your vicinity, the gravitational pull of those galaxies is going to disturb the structure of your home galaxy. And that's one of the unique features of our Milky Way galaxy. It's in a tiny enough cluster where the members are well enough dispersed or separated from one another that we don't get these kinds of tidal distortions that would rip apart the structure of the spiral arms of our galaxy.
This is called the Virgo cluster, if I'm not mistaken.
Well, the Virgo cluster is the nearest supercluster to our local group. But if I could talk a little bit about our local group, it's only got 24 members in it, and only 2 of the galaxies are even medium size. It's our galaxy and the Andromeda galaxy.
That are the largest.
Right. I think we got a visual of the Andromeda galaxy, and it's quite similar, a little bit bigger than our galaxy, but a spiral just like ours. But all the other galaxies are dwarf galaxies. I think M33 is kind of a medium
It's
small.
a medium-sized galaxy. It's fairly large, but it's not too close either.
It's not close.
Yeah.
So the short answer is that we live in a place where we're close enough to big galaxies that we've got enough material, but we're on the outskirts so that we're not involved in all the gravitational give and take.
Right.
So we're stable.
And Jeff, that's a good point, because if you don't have enough close by members, there's not enough gas and dust being fed into your galaxy to sustain ongoing star formation. So it works both ways. You want to be in a cluster that's dense enough that there's this flow of gas and dust to sustain ongoing star formation, but you don't want to be in a cluster that's so dense that it disturbs the structure of the spiral arms of your galaxy. And most galaxies are in a spot where there's too many other galaxies disturbing it. But our local group has the good feature that it's on the extreme outer fringe of the Virgo supercluster of galaxies.
So we have fine-tuning then in the particular cluster of galaxies that we're in. Then the next point that we wanted to talk about was the type of galaxy itself.
Right.
And I think we have some overheads here that show pictures of various galaxies. First there's the spiral galaxy, which this particular one is a very uniform, very beautiful looking spiral.
Right.
Not much going on in there. Here's the elliptical galaxy.
And the vast majority of galaxies in the universe are these ellipticals.
Is there a percentage on that figure?
Well, it's like 90% or
90%
more of the
are
galaxies
elliptical.
are elliptical.
That's because all of the star formation has ceased to take place in those
Right.
galaxies. So they may originally have been spiral galaxies, but now there's no star formation taking place.
Well, except for these special interaction situations, the galaxies are all about the same age. They were all formed early in the history of the universe. But for the vast majority of the galaxies, star formation has ceased.
Right.
And so they collapse into these elliptical structures. Only about 6% are spirals at this point in cosmic history. And then you got the irregulars. And these irregulars are these disturbed galaxies.
Well, we have a few more pictures here.
Oh,
There's
good.
a spiral galaxy.
There's an irregular right here.
Okay, Centaurus A, an irregular galaxy. Do we have any more spiral? There, yeah, the Whirlpool. It's a very beautiful spiral. That was one that, in fact, I studied in the hydrogen line.
One of my favorite ones to look at through my telescope.
Now, the Sombrero galaxy, that's the name of it, of course. That's a spiral because it still has the disk there.
Right, but a very large central bulge.
Right.
Yeah.
Now, the question is, here's another beautiful spiral galaxy. In fact, I think that's the Andromeda galaxy,
That looks like the
if I'm not
Andromeda galaxy.
mistaken. Is what is the just right or the right type of galaxy for, what do we need? What are the parameters?
Well, the problem with the irregular galaxies is they're highly disturbed, and a lot of them are too small. You need to be in a galaxy that's big enough that it's not going to be beat up by neighboring galaxies. But you don't want the galaxy to be a supergiant one. Supergiant galaxies have the property that they condense so much gas and dust towards the center that they form these giant black holes, and these giant black holes blast the entire galaxy with radiation that would be deadly to life.
Very difficult, yeah.
And so the ideal size of a galaxy would be, say, medium-large, which again kind of narrows it down to less than 0.1% of the galaxies would therefore
Yeah, I
be
think we
candidates
have
for life.
we have a picture here of what would we consider a just right galaxy, that it would be a spiral galaxy,
Right.
and there
Well, the
are only
reason for spiral is that it's spiral galaxies that have ongoing star formation. And to get a star like the Sun and a planet like the Earth, you need 3 separate generations of star formation. So like with the ellipticals, you've only got 2 generations of stars, and that's not enough to get the kinds of stars and planets you need for life. The spiral galaxies are where you're going to sustain this long enough to get the kind of bodies.
stability and
that
the
you would
kind
need
of
for life.
material that you need.
So it must be a spiral. That's only 6% of the galaxies that currently exist.
Right.
It must be a medium-large size galaxy. And then it must be in the right location of the universe, a fairly sparsely populated part of the universe. And then the size of the bulge is critical.
Now that kind of gets us to the next phase, doesn't it?
Yeah, we
Okay.
had the location relative to the other galaxies, the type of galaxy itself, and then what does the galaxy look like on the inside?
Yeah, what's the
So-
kind of internal structure of the galaxy?
Yeah, and
Right.
Hugh pointed out earlier, we were looking at the Sombrero. It had this, I mean, most of the galaxy, you could see the disk, but there was this very large bulge part of
Yes.
it. And it turns out that if the bulge is too large or too small, you run into problems.
Right.
The bulge being too large, you end up with this too much radiation coming out of the center. If it's too small, you just don't have enough gas there to form the planets.
Well,
and
like
the
with the
stars.
Sombrero, the bulge was so large that it'd be impossible to place a star anywhere, even in the outer spiral arms, where it wouldn't be blasted by radiation from that bulge.
Right.
If you make the bulge smaller, then you could put the Sun, for example, in the plane of the galaxy, where the dust in the plane would protect it from the radiation from the center of the galaxy. And by the way, it's one of the unique features of our star is that it doesn't move up or down in the plane very much, and therefore doesn't get blasted by the bulge.
Right.
But the other end of the coin is you have a problem with the bulges too small. Spiral galaxies with small bulges are not dragging in enough gas and dust from the gobbling up of dwarf galaxies to get the material that you would need for a planet like the Earth out to the just right spot. We're going to cover that later. But the solar system can't be too close to the bulge or too far away from the bulge. There's a certain distance where life is possible, but it's important that you get the heavy element material out to that just right location within the spiral galaxy. If the central bulge is too tiny, that's not going to happen.
So you don't have enough of these stars going supernova and populating the outer parts of the galaxy with enough heavy
bringing
elements.
about the extra material and the heavy element material. That is. What's the relationship between these large bulges and the idea that there's a black hole at the center of galaxies?
Well, it's really the density of the bulge that will determine how big a black hole you get. But yeah, the bigger the galaxy, the bigger the black hole at its core or its center.
Okay.
The bigger the bulge, or the denser the bulge, the bigger that black hole will be.
Now, do we believe that there are black holes in the center of every galaxy?
The center of every big galaxy, yes,
Okay.
we believe. And one of the features of our galaxy is that it does have a black hole, but it's not too big. We have a relatively small black hole in our galaxy, which is essential for life. Most galaxies our size would have bigger black holes, which would be a problem.
Okay.
So we'll pick this up
All
next
of this
time.
is fine-tuned.
That's right. Welcome to Reasons to Believe, the television program where we explore new reasons, new evidences to believe in Jesus Christ as Creator, Lord, and Savior, and new reasons to take the words of the Bible as the error-free communication from the Creator of the universe, not just for faith and practice, but for all disciplines upon which the Bible touches. And we're in a series that deals with what's called the cosmological anthropic principle, the concept that the universe has been fine-tuned, purposely designed to create an environment in which human beings can exist, that the universe really exists for the support of human beings. And we've been kind of moving, gentlemen, from the gross features of the universe, the constants that govern the characteristics or the governing of the universe, and moving on into the structures of the galaxies. We're going to talk about stars. And we've been asking you for your comments, and we appreciate the letters that you have been sending in. They really do help us to structure these programs. And Dave, I think you got another letter from one of our constituents.
Yes, we have another one of these encouraging letters. It says, "Hi, Reasons to Believe team. Just to reiterate how much we look forward to and appreciate your ministry. There should be more programs like this to reach the heart through the intellect. I have been indebted to C.S. Lewis's writings for 50-odd years, and now your program has stimulated and blessed us both." This is coming from Viv and Wanda, who live in the Republic of South Africa. So we're reaching quite a long distance here around the world.
Well, we really have been benefiting from the Trinity Broadcasting Network's expansion overseas into Europe and Asia and South America and Africa. And we do get quite a few letters and emails from those different countries. And we really would appreciate those of you that are watching this show to thank Paul and Jan for their generosity in keeping us on the air here at TBN. This show wouldn't exist without their giving us time on their stations to do this. So do write them a letter of thanks. And if you've got suggestions about how we can improve this program or tell us what you like about it, that really helps us in structuring future episodes. Well, gentlemen, we're on the topic of the anthropic principle. And we've been kind of moving from the large features of the universe,
The big picture.
the big picture, and kind of picking up the details. And there's a reason why we're taking this approach in this series, is that, when in terms of looking at the gross features of the universe as a whole, we're not able to make the measurements with the same degree of precision as objects that are up close. And so by starting with the big picture of the universe, its gross features, and kind of moving down towards things like galaxies and clusters of galaxies and stars, and then solar systems, planetary systems, what we're wanting to reveal is that the more detail in which we can examine the systems, the greater the design evidence we're seeing. It's one of the ways to put this anthropic principle idea to the test. The more we learn, the more we see, the greater the precision of our measurements. Are we seeing the evidence for design dissipate, or are we seeing the evidence for design increase? And by taking this approach, we can put that to the test. If you've missed the last few episodes, they are archived on our website at reasons.org. So we're not going to review what we covered in the last 3 episodes. You can go to our website and either view or listen to the previous programs. And of course, it's covered in other resources as well. That's at reasons.org. The theme for today's discussion is stars. We're not so much focusing on the sun, but let's look at stars
in general.
And what kinds of stars, what types of stars do we need for life to be possible?
Yeah, one thing, looking over our topics for today, it seems that it's all it's all tied together by, if you're going to have advanced life, you need to have particular types of elements. In the Big Bang, we produced a lot of hydrogen, quite a bit of helium, but you're going to make people or even ants and grass, you're going to need carbon and oxygen and nitrogen and heavier elements. And so we're going to look at how you form stars, what sorts of special stars and how they produce those various kinds of elements.
Well, that's an important point, Jeff, that in creating the universe, you're creating the universe. I mean, as we pointed out earlier, the idea of the Big Bang really is a biblical concept. The Bible speaks about this transcendent creation event in which the universe continuously expands. Well, in an expanding universe, you're going to get different conditions at different times. And as the universe cools down from this very high initial temperature state, it passes through a window in which nuclear fusion can take place. And so the universe that began with only the element hydrogen, within 4 minutes after the creation event, because of this fusion episode, becomes transformed into a universe of 75% hydrogen and 25% helium, and only trace amounts of things like the light elements, deuterium and lithium and tritium, and everything else. I think there's a tiny amount of boron and beryllium that's made too.
Some of the very lightest.
But things like carbon, oxygen, nitrogen, iron, silicon, all of that doesn't happen in the Big Bang creation event. Those elements are manufactured later, after the Big Bang, in the first stars that are formed and the stars that form after the first stars.
We have a picture here that kind of shows the life cycle of stars, how they're starting out being formed as new stars in some of the places in the galaxy where star formation takes place, where there's a lot of gas and dust. This is within the spiral arms.
Yeah, anywhere where you've got gas and dust that's reasonably collapsed, it's going to lead to pockets within that gas cloud where the gas and dust density is enough that gravity takes over and the gas and dust begins to collapse to form a star. So that's how stars form.
Right.
And astronomers see star formation going on all throughout our galaxy and in other galaxies as well.
Now, we sometimes use the word birth to refer to this star formation, but we want to make sure people understand that the birth here is not the same as someone biologically being born. But you have a little analogy that you like to use.
Well, there's no animation for a star.
Mm-hmm.
I mean, when physicists talk about star birth, it's really no different than another group of physicists talking about raindrop birth.
Right.
I mean, raindrops form actually in a similar way to stars. It takes some departure from thermodynamic equilibrium to stimulate this seeding of a new raindrop, just like it does for the seeding of a new star. And then you have these water molecules that collect to the seed point, and this droplet grows and grows until it reaches a point where gravity causes it to fall to the earth. And that's sort of the birth of a raindrop, the evolution of the raindrop thereafter as it grows.
Some part of its life cycle.
And that's really what atmospheric physicists mean by the evolution of raindrops, is simply the growth of the raindrop.
Right.
And then the raindrop dies when it hits the pavement in your backyard.
In your backyard, and it ceases to become an individual drop.
Exactly.
So here we have stars that are, through gravitational attraction, now the material that's present in the spiral arms of galaxies is now bringing about the formation and eventually the evolution of that star. That star's change as a function of time.
Well, typically astronomers refer to the birth of a star as that moment when the gas and dust has collapsed enough that has driven the temperature at the core of the star to the point where nuclear fusion's ignited.
Here we have a picture here showing some
So
of that birth.
here's the
part of the
collapse
thing.
taking place, and as the material collapses and the star becomes smaller and smaller, the star cloud, the temperature of the core goes higher,
Higher
and
and
higher.
higher. Yeah.
And when it hits 17 billion degrees centigrade, it ignites the hydrogen bomb mechanism. And this is what causes this burst of light to come out from the gas cloud, and we call that flash point the birth of a new star. Now, actually, we can see the star before that flash point, because as this gas and dust is collapsing, it is heating up the cloud, and you begin to see light. But there reaches that point where this hydrogen fusion takes place.
Nuclear burning that begins.
And now you have a stable burning star. But during the stable burning phase, we have stars. All stars will become more and more luminous over time in this stable burning condition. Now, it's not dramatic. I mean, the sun today is only 30 to 35% brighter than it was when nuclear fusion was
first was
ignited
born,
some 4.5 billion years ago. But there reaches a point when the fuel, the hydrogen fuel, is being fused into helium and other elements. That fuel runs out. And when it runs out, that's when the star goes into its death stage. But when we talk about star death, it's no different than, say, a log on an open fire that's been all burnt up.
Burnt out. And finally, it just stops burning.
And when it's in the ember stage, we call that the death of the open fire.
Now, it's a good thing that a log, when it burns out, doesn't do the same thing as many stars do when they burn out.
Right.
Because the next phase of the star is what we call
A supernova.
supernova. It's
Right.
a huge explosion.
Right.
Well, it is important to point out, not all stars go supernova. I mean, there needs to be a fairly massive star for it to go supernova.
Yeah,
But,
that's what I understand. Yeah.
Well, that's the whole problem. We talked about the fine-tuning of the different constants of physics and the laws of physics. You need that fine-tuning to get a suite of stars. I mean, in order to have life existing in the universe, you need these big stars, you need the medium-sized stars, and you need the small stars. You must have the whole suite. The really big stars are the ones that go supernova. And the reason you want supernova, it's only in supernova-type stars that you're going to get the production of these very heavy elements heavier than helium in a dramatic manner. And moreover, when a supergiant star ends its life, it ends its life in a cataclysmic explosion. And that explosion has the effect of scattering the ashes from the burning cycle of the star to the interstellar medium. And it's the throwing out of those ashes into the interstellar medium that allows for the opportunity of a second generation of stars to form, that form out of the
Out of that
hydrogen, the
material.
helium, and the ashes of the
Ashes.
previous generations of stars. And now you get a star with a very different burning capacity than the former generation.
It's going to be a different type of star.
And if you want planets and moons, I mean, both the moon and the Earth are essential for human life to exist. And to have these planets form, you need a certain minimum amount of these ashes to be incorporated into the star. And actually, astronomers have determined that planets like the Earth and bodies like the moon are not going to be possible until you go through at least 3 separate generations of stars.
I think we have an overhead that shows these 3 different generations
Right.
here.
So,
To just go through that, the first generation stars are somewhat peculiarly called the population 3 stars, typical astronomers here. And that deals with elements that are, say, heavier than helium here. And then the second generation star is the population 2, and their elements heavier than helium, 2%. And then the third generation star, of which our sun is an example, the elements heavier than helium are present
right.
to a certain percentage.
And the reason for this strange system of naming population 1, 2, and 3 The first stars that astronomers ever observed were the population 1 stars. And these are the stars that are nearby.
The bright stars.
But they're the stars that formed when the universe was relatively old. And so they'd be late forming stars. And then when you got more powerful telescopes, we were able to look far enough away that we could see these population 2 stars, which formed much earlier in the history of the universe. And then the last were the population 3. In fact, astronomers really cannot give you an exact example of a population 3 star. We can come really close. And maybe some of the research you're doing, Jeff, shines light on this, in that astronomers have seen hypernovae, and many of them feel that the hypernovae indeed are true population 3 stars.
That are exploding then in these...
Well, the way the physics of the universe operates is that when galaxies are young, the first stars that form are these really massive stars. Some think they may be even 200 and 300 times the mass of our star, the Sun. And these would be stars that would form out of the primordial material.
Hydrogen and helium.
Essentially only hydrogen and helium. And because of that, only the biggest stars can form. Well, the problem in terms of detection is the bigger the star, the faster it burns. So for example, as you look at stars in our solar neighborhood, we have really small ones that are, say, like 1/10 the mass of our star, the Sun, and they take 50, even 60 billion years to go through their burning cycle. A star like the Sun, which is kind of medium size, it takes 9 billion years to go through its fuel supply. But a really big star, say like the star Sirius, goes through its fuel in just a few million years. But these population 3 stars, which are much bigger than the supergiant stars in our solar neighborhood, 200 and 300 times the mass of the Sun, rather than just say 5 or 10 times the mass of our star, the Sun, they literally burn up in just thousands of years. Now what that means is they're going to be virtually impossible to detect today, because these are stars that would have gone through their burning cycle very early in cosmic history. You're looking at a time window only a few thousand years wide, and that really explains why astronomers see so few of those stars. They burn up very quickly, explode their ashes to outer space. But these hypernovae that we're seeing in very distant galaxies, galaxies that were shining and we're seeing their light from billions of years ago, very likely are these population 0 metal type stars. Astronomers, however, have seen small stars that formed immediately after those first stars. They have very little in the way of elements heavier than hydrogen and helium, and that tells us that they must have formed right after.
Now, are these smallest stars the ones we called white dwarfs?
No.
They're not the white dwarf. They're just a... Well, go ahead.
Well, I mean, you'd have to pick on really small stars and see. The smallest stars can't form in the very beginning. Only the really big ones can. But after you get these 200 and 300 solar mass stars forming and exploding their ashes to outer space, now for the first time you can get small stars forming. The ashes.
From the ashes. Okay.
The ashes stimulate the possibility of small star formation. And the smallest of those stars will still be burning today, which means we can see them. So if you can find these small stars that formed right after these really big stars formed, that gives you a picture on that episode literally just thousands of years after these population 3 type stars burned. But we're kind of getting off track here.
Right. Now,
So we've got this process where stars are born, but it takes 2 or 3 generations of supernova, which you need the supernova to produce the carbon, the nitrogen, oxygen, the heavier elements. Basically, the generations give you more than just hydrogen and helium in the universe.
Right.
And then you need other types of stars actually to produce all the elements that we need, such as the fluorine that you can generate out of white dwarfs.
Well, I mean, in terms of...
here's a graphic showing you most of the elements that you get out of a supernova explosion.
Right. You get silicon, you get silver, phosphorus, copper, potassium, nitrogen, carbon, oxygen, etc. And the whole point there is, if you want a planet that will provide a home for life, and human beings in particular, you need more than 6 or 8 different types of elements. You really need the entire suite of elements. And particularly advanced life needs heavy elements. We need arsenic. Arsenic's a deadly poison, but you need at least a little bit of it in your diet or you're not going to live. And also we can suffer from silver poisoning if we don't have enough silver.
Or lead is a more common type of poisoning. Or,
right.
Or mercury poisoning, for
well,
instance.
what I'm talking about are these vital elements, these vital poisons. Because whereas mercury is deadly in almost any quantity and is not something that's built into proteins, chromium is an example of an element that we must have to get the proteins so that we can function. But too much chromium will kill you. Too little chromium will kill you. Well, what is it going to take to get a planet, a planetary system, where we're going to have the right suite of elements in the right abundances so that human beings can exist at this moment in cosmic history? And one of the things astronomers have discovered is that there are different kinds of supernova. You've got maybe 6 or 8 different kinds, but they fall into 2 basic categories, the type 1 and the type 2. And the type 1s make a different suite of elements heavier than iron than the type 2. And for life to be possible, you need contribution from both
of
kinds of supernova. Moreover, what we're seeing in the solar system is a system of a star and planets that are relatively old. In fact, one of the things that astronomers have noted is our solar system is probably the oldest such planetary system that exists in our galaxy or the universe. Whereas it's rather common for stars forming today to be having planetary systems. This is rare when you get to systems as old as our star, the sun. And the whole point here, Jeff, you were making the point that as the universe gets older and older, the quantity of ashes gets greater and greater.
Larger amount.
And so we would expect that the youngest stars would have the most material, ash material, for making planets, whereas the older stars would have less. But in the case of the sun, if you want our sun and our solar system to be enriched enough with elements, it's necessary that they form in a special way. The sun must form adjacent to a supernova eruption. And if it forms too close, then the supernova will destroy the sun and its planetary system. But if it forms too far away, there will not be enough heavy elements put into the solar nebula to get the stuff you need for life.
And that type of supernova probably has to be correct also.
Well, you need both a type 1 and a type 2.
Within the neighborhood of this solar system.
Well, often astronomers call this the amazing double coincidence, that the sun had the good fortune of forming at just the right distance and just the right time relative to 2 different kinds of supernova eruptions.
It's quite remarkable.
Well, I mean, that was part of your research, Dave, that supernova aren't that common.
That's right.
It's like once every 50 or
30
100
to 50 years, yeah,
right?
somewhere in that range.
And we're talking in an entire galaxy.
Now, of course, earlier in I suppose the earlier universe had more supernova going on than we see today.
Yeah, the figures I've heard
areas
are like when the solar system was forming, it might have been as high as 20 or 1 supernova every 20 years.
Yeah, so it's
whereas
not
today
that
it's
much
more
higher.
like once every 100.
So, but to actually have been fortunate enough to be in the right place at the right time to get 2 supernova close together to where our star was
Right. Not too close, not too far away, not too early, not too late,
Right.
in order to get these heavy elements mixed in. And the whole context here is that God is trying to quickly prepare a solar system, a planetary system, where life can exist.
So what we're kind of saying then, to kind of reiterate here, is that we have stars being born in the presence of all this gas and dust, and then we have that star developing and then going supernova. And there is some of these heavier elements made within the star as the star evolves and cooks, as it were. But a lot of the material, a lot of the heavier elements as I understand it, is made at the actual time of this explosion.
Right.
When the explosion occurs, there's high enough temperatures to bring about the creation of these heavier elements.
Anything heavier than iron
Everything heavy. Okay, that's a
is
good
made by supernova.
going on within the supernova, and then that, in turn, forms the material out of which the second generation, and finally a third generation, is made. And it's that third generation material that has the elements necessary to make the kind of planet that we have and the kind of elements that we need for life.
Well, there's one other kind of star you need to make this work, and that's a particular category of white dwarf binary.
Okay.
And these would be two burnt-out stars that are kind of in their ember stage. Right.
Dwarf.
These are white dwarfs. What we're talking about are two white dwarfs that are close enough together that you get a gravitational interaction where material is being stripped off one and dumped onto the other. And a certain category, fine-tuned category, these white dwarf binaries, will efficiently make fluorine on the surface of one of the white dwarfs and then expel that by a strong stellar wind into the interstellar medium.
Oh, okay. So it's not a supernova explosion.
The supernova don't make fluorine.
Okay.
You need these white dwarf binaries to make the fluorine, which means that in terms of our solar system, it must have the good fortune of forming right next to a type 1 supernova, a type 2 supernova, but also have the benefit of these nearby white dwarf binaries that are sending in enough fluorine so that you get the right mix of chemicals so that planet Earth and the Earth can have the elements that are necessary for life.
So why do stars have to die? And this is one of the questions that frequently comes up.
Well, just like you need plants and animals to die before human beings can live, likewise we need stars to be dying before we can have the birth of the sun,
giving off these
with the right elements that are necessary for
right.
life.
So it's a very important process that's going on here.
Right, and it has to be incredibly fine-tuned in order for life to be possible. Welcome to Reasons to Believe, the television program where we explore new reasons, new evidences to believe in Jesus Christ as Creator, Lord, and Savior, and new reasons to understand the words of the Bible as the error-free communication to humanity from that Creator. And what we've been doing these past few episodes is examining what's called the anthropic principle. This is the concept that the universe has been purposely structured, fine-tuned, or designed to provide a habitat for human beings. And if you've missed the last several episodes, they're available on our reasons.org website. You can either listen to them or view them in live streaming audio. So check that out. There's other resources there that deal with the anthropic principle as well. And we really do appreciate any feedback that you might be able to give us. As I've mentioned before, we're trying something new in this series, bringing on 3 scholars in the same discipline. I'd like to hear from you how that's working out from your perspective, because it's something we might be able to use in succeeding series that we do here at Reasons to Believe. But Dave, I think you've got a letter from one of our constituents.
Yes, I do. We're always grateful for the communications that people give us here on the show. This is an email. It says, "My wife and I want to tell you how much we appreciate and respect the ministry of Hugh Ross and his Reasons to Believe team. They exhibit not only scientific expertise that is obviously genuine, but they are wonderful examples of godly character. Thank you for airing such a godly program that is reaching people in the scientific community that Debbie and I could never reach." And this is coming from Gary and Debbie, and they live here in California in Coarse Gold near Yosemite.
Well, we hope this is a show that reaches out not just to scientists, but to lay people as well. In fact, we'd appreciate hearing from both people that do have an education in science and those that do not, as to how well we're reaching both audiences. And do take time, too, to thank Jan and Paul Crouch for our privilege of being on the air on their Trinity Broadcasting Network series. I think a word of thanks to them would be very appropriate, as their generosity allows this program to continue. Well, We've looked in our series on the anthropic principle on the features of the universe, galaxy clusters and galaxies, and the kind of what you need in terms of stars, how you need to have a whole suite of stars, big stars, medium-sized stars, and small stars if you want a sun and a planet like Earth. But I think the thing we want to focus on in this episode is the sun, the special star,
One particular star
or sun. And yes, the sun can't exist unless there are big stars and small stars to accompany it. But what's special about our star, the sun? And there's a few things we plan to review here in this program about the sun. We want to look at its age, its mass, its metallicity, how many metals there are that are heavier than hydrogen and helium, the type of star, the solar flaring and sunspots. These are just a few of the features. In fact, I've got one book here called The Rare Earth. This book written by a couple of non-Christians, interestingly, Peter Ward, who's a paleontologist, and Don Brownlee, who is an astronomer. And even though neither of them are Christians, they do talk about what a special kind of star you need and a special kind of Earth, similar to what you see in our writings. But I think we ended our last episode with the point that our sun is a relatively old star. It's about halfway through its burning cycle, which incidentally itself is interesting. If you want human beings to exist on a planet orbiting a star, you want it to be orbiting a star that's halfway through its burning cycle. For the simple reason that's when stars are in their most stable state.
Right, in terms of luminosity and any other activity.
Well,
it could disturb life on Earth if it weren't in that stable phase.
One of the astronomers that does volunteer for us, Guillermo Gonzalez, his research team has made note of the fact that when stars are young, they flare a lot. And when they're old, they flare a lot. When they're young, their luminosity is not as stable as it is when it's middle age. Likewise, when a star gets older, its luminosity begins to vary. And so when a star is in its most stable phase in terms of a steady luminous light that comes out is when it's precisely middle age. And that's when it has the least intense and least numerous flares.
Now
So
we're talking about a sun that is about 5 billion years old now. And typically this kind of star would burn for 10 billion years, something on that order?
well, the sun has a capacity to burn by the hydrogen bomb mechanism. There are other mechanisms that kick in after that. But in terms of the most stable fusion burning process, that can be sustained for 9 billion years in a star as big as the sun. And we're going to talk about why it must be exactly the size of the sun. So the size of the star determines how long it will burn. But for all stars, their most stable phase is when they're precisely middle-aged.
And I don't know that we're going to talk about it, but I do recall reading somewhere that our star is remarkably stable even amongst other stars that are about its size.
That's true.
Its luminosity does not fluctuate as much as most of the other stars its size that we see.
Yeah, solar-type stars that we see have more dramatic flaring than the sun. But it could be that these other stars we're looking at aren't exactly the same age as the sun, so that might be the explanation. The mix of elements we know is a little bit different. That might be part of the explanation. But the whole point for human beings is this, is that whereas bacteria can tolerate a fair amount of solar flaring and still survive,
Variation in the luminosity of the sun.
right, and these intense flares that come off, bacteria can handle a fair amount of that. Human beings cannot. We're very sensitive to.
We could get our sunburn in a matter of a few seconds here if we went out in this kind of an environment.
Well, here's an example of a solar prominence. Those little hot spots are associated with solar flares. And these can be pretty nasty because they have a lot of radiation attached to them. It's something that NASA is very careful to watch out for when they send astronauts to the moon. You don't want them to be going to the moon during one of these flare episodes because the radiation would be harmful for them. But I find it an interesting observation that God creates human beings on planet Earth at the precise moment when the sun
this
is
is
in
the
its
most stable
Exactly.
position that it's in.
He creates the bacteria earlier because he knows those bacteria will give us a lot of resources that we need for technology, and they can handle the flares. We can't handle the flares, so we get created late. So when people ask me the question, well, why do we see in Genesis 1 God creating the primitive life first and the advanced life second? The sun's got a lot to do with it.
Yeah, the stability of the sun.
Right.
We kind of have three different characteristics that are required for our sun. I don't know if we showed that overhead yet, but there's the fact that it's late born, that it's third generation, I think you said.
Right.
And that it's a bachelor star.
Right.
And maybe we could talk about that for a moment.
Right. Well, we mentioned in our last episode that the sun is a third generation star or a population 1 type star. But we discussed at the end of that last episode how the sun had the good fortune, or you could say purposeful design, of forming right next to a type 1 supernova eruption, right next to a type 2 supernova eruption, and close by to a special kind of white dwarf binary that would produce all the elements that are necessary for advanced light to be possible on a planet orbiting that star. And how, as we look at the quantity of elements heavier than helium in stars in our galaxy, the sun has a very high amount of these heavy elements, about 3%. But it's not 3.5%.
Mm-hmm.
At 3.5%, the forming planetary system will be so filled with junk. What I mean by junk would be comets, asteroids, and dust that would pelt all the planets and pock them with light-destroying events. So you don't want that metal abundance to be too high, but you don't want it to be so low that planets and moons don't form. So there's a just right amount of metals or elements heavier than hydrogen and helium that you need. But I think one of the unique features of our solar system is I don't know of any other star that has the quantity of elements heavier than hydrogen and helium that is as old as the sun. We do see stars with more of these elements that are young, but in fact nearly all young stars have these dust or planetary systems going around them. But what's special about the sun is that it's got so many of these elements heavier than hydrogen and helium for its age. And of course, age is critical in terms of getting human beings on the planet
Now,
at the right
remind me
time.
the importance of having the right metallicity, the right amount of this material.
Well, there's two reasons.
Two reasons.
It needs to have enough of these elements that you're going to get planets and moons forming.
Okay.
But you don't want it so high that you have all this
okay.
debris
All right.
running
the
in
extra
here,
debris.
causing these collision events.
Now, of course, there was a lot of debris in the early solar system.
Right.
That was the cause of all of the, like the
moon forming,
yeah,
for example,
yeah,
right?
the meteor patterns on the moon, and the other planets as well.
Right.
So in the early solar system, there was a lot of material, but it quickly got cleared out.
Yeah, you don't want it persisting to this day.
Yeah. Of course, that's what we're fearful of today, is it not?
Right.
That one of these things is going to hit the Earth.
Well,
and,
to go back to
and
the
life.
bacteria, bacteria can handle a lot more of this debris disturbance than advanced life can. Another reason for what we see in Genesis 1 and Psalm 104, God creates the primitive life first, the advanced life second, and we get created last at the very end of the line.
In fact, I think that's, if I remember, you look at the major extinctions, or most of them seem to be tied to asteroids or comet impacts. That,
Right.
The advanced life, the things that fossilize well and that we can see, get wiped out pretty easily when that happens.
Right.
But it's clear that there's still life there. So.
Well, there's a third factor in all of this, Dave and Jeff, and that is that you want a planet that not only has these elements heavier than hydrogen and helium, you want to make sure you got the right abundances of these vital poisons, chromium, molybdenum, silver.
We talked about that in
right.
our last program.
And you also need uranium and thorium in the Earth, because that's going to be critical for driving the life-essential plate tectonics. I think we'll talk about that in our episode on the Earth.
Yeah.
But the whole point is
All of these things.
these elements heavier than hydrogen and helium need to be critically balanced for every single one of the elements in order to get the right environment where human beings can exist.
So kind of looking at our list there, we got the age that you need to be born
Right.
early enough in the galaxy that you're not going to be just completely swamped with metals,
Right.
but you need to have a particularly metal-rich star. So you need to have a star that's large enough to have
Right.
to collapse a lot of that in. Just again, it seems like you start stacking up lots of things that need to be true to get where we need to be today.
So the metallicity must be just right, and that's a term for elements heavier than hydrogen and helium. And the age must be just right. The third factor you have to fine-tune is its mass.
Mass.
The mass must be just right. And as we discussed in the previous episode, the universe and our galaxy are filled with stars of all different types. The smallest stars are 8% the mass of our star, the Sun. The biggest stars that exist today are like 20, 30, 40 times the mass of our star, the Sun. Although those are really quite rare. I mean, what we call supergiant stars are more typically 3 to 10 times the mass of our star, the Sun. But there's a reason why you don't want to be orbiting a giant star. I mean, we have our planet Earth orbiting a giant star. The problem with going with a giant star is it burns up rather quickly, and it burns up in a way where the luminosity isn't very constant. And moreover, the planet would now have to be orbiting a long distance away to be kept at the right temperature. You'd have flaring problems. And so the bottom line is you don't want to be going around a big star.
So basically just never achieve the luminosity stability of a smaller star like
you will
we are.
not get the luminosity stability that's necessary for life.
So
Giant
I
stars
think
burn
we
up
have
quickly and erratically.
So we have kind of a graph here that shows the just right star
Right.
in terms of if it's too massive, then it's hotter, burns up fuel faster, and more erratically.
Right, right. But the problem with going with a star smaller than the Sun is the stars smaller than the Sun are much fainter than the Sun. And that means that it's going to be necessary to take your life support planet and pull it closer to that star to keep it at the temperature for life. And the problem with bringing it closer to the star is the tidal forces go up with the inverse fourth power of the distance separating the star from the planet. And that little bit of mathematical jargon simply translates into the fact that, well, actually, let me just explain it a little bit.
Well, it's kind of like the fact that the moon, very much less mass than the sun, has as much or similar kinds of effects tidally as the sun does, which is very much further away, but
Right.
more massive. So that kind of gives you a feel for being much closer, gives you a lot more tidal effects.
Well, let's look at the Earth-Moon system. And maybe this is a little bit better, a little more to scale, okay?
Okay.
Here's the Earth, and here's the Moon, all right? Now, the gravity of the Earth operates in such a way that it's going to pull much more strongly on the near side of the Moon than the far side of the Moon. And that's the reason why the Moon maintains the same face to the Earth as it revolves around the Earth. The tidal force is so strong that it actually pulls this one side. In fact, it's so strong that the Moon's surface bulges up 150 feet towards the Earth.
Further out.
We have tides of a few feet of water. The Moon has tides of 100 feet of solid rock.
Okay.
So, but when you're talking a planet and its star, these tidal forces will now operate. If you bring the planet a little bit closer to the star, the tidal forces now become strong enough that the star will pull a little more strongly on the near side than the far side in such a way as to slow down the rotation rate.
Okay, so it has an effect.
And in terms of our own solar system, that's happened to Mercury and Venus. Those planets are close enough to our star, the Sun, that the Sun's tidal forces have break the rotation period. And you know what? For Mercury, it's like 90 days. And for Venus, it's like 250 days that they take to make one rotation.
It's really slowed them down significantly.
Well, you can, yeah.
So the net effect is that though you can decrease, or if you decrease the mass of the star, just because you move it in doesn't mean you're in the same condition. You've got this this other condition that's going to really mess up your orbits.
It's going to really mess up the rotation rate. And obviously you don't want a long rotation period because that's going to make it very hot in the daytime and extremely cold at night, which light can't tolerate.
We have this summarized on this picture here. The less massive planet is providing a cooler, it's a cooler star, and then it causes the slower rotation speed for nearby planets. That's what you were just talking about.
And one more factor we can add to that is if you go with a smaller star, its flaring is much more intense and numerous than it would be for a star like the Sun. So the Sun really is the Goldilocks kind of star.
Really the
just the right mass where you got the minimum flaring, the greatest stability, and you can put the planet at the just right distance from that star so that you don't run into the kinds of problems you would with supergiants or small stars.
I imagine if you were too big and too far away, your tidal activity probably would not be quite enough either.
It wouldn't be quite enough, yeah, because after all, our planet began with a rotation rate of about 6 hours a day. And if it was any further away from the Sun, it wouldn't slow down. And 6 hours a day is okay for a bacterium, but it's not okay for a cow, pig, or horse. The wind velocities would kill any large creature.
Right.
I can't resist making the comment that many would then say, well, if the Sun were any different, the Earth were, at a different place, the Sun were larger or smaller, then we wouldn't be here to make these observations about this planet going around this Sun. That's kind of their explanation. This is, I think, what they call the weak anthropic principle. The idea that if things were tuned any differently than what we're talking about here today on these shows, then we wouldn't be here to see these things.
Right.
But that's not really an explanation. That's just an observation.
It's just an observation.
Yeah, we wouldn't be here. Yes, that's correct.
And I think we've got a future episode coming where we're going to deal with all the rebuttals to God being the one that's responsible for all his design.
Right.
But you're bringing up a good point, Dave. The rebuttals are philosophical in nature rather than scientific in nature. So, but we have some other characteristics to discuss as well.
I like the idea that you got to have a bachelor star. I think the common view of people, and for me for a long time, was that you just got all these single stars sitting out there, when in reality most stars, from my understanding, are formed in binary systems where you've got 2 stars or even 3 stars orbiting,
or 4 or 5 even,
mutually around one another.
Right.
Binary star right here.
In fact, I just recently watched Star Wars, and Luke Skywalker had 2 suns out there. This idea that you can have life around multiple stars.
Well, it's possible to have planets around multiple stars. I mean, to take this as an example, where you got a big star and a small star, and you got a planet orbiting them. If you're very careful about positioning the 2 stars relative to one another, it is possible to get orbits of planets around the stars that don't get kicked out or gobbled by one of the stars. Possible, not probable.
Yeah, very unlikely.
Much more likely is the fact that the 2 stars are going to gravitationally interact to disturb the orbit. But when you're talking about the possibility of a life support planet having a stable orbit that stays within what's called the habitable zone, now you get a 0 probability if it's a double star system. Put 2 or 3 stars into the system, you might have a Jupiter, a planet the mass of Jupiter, in a stable orbit around the 2 systems.
Some distance away.
Distance away, it might work. But a planet as small as the Earth, close enough to any one of the stars where it would be at the temperature that would be suitable for advanced life, the other star inevitably will disturb its orbit and kick it out of the life support zone. So planets are possible around double and triple stars, but not life support planets.
A question that comes up, there's a lot of research going on trying to discover planets going around other suns. They are selecting these stars by looking out there? Are they selecting stars that are similar to our own sun?
Yes.
So this is the ones that they're looking at the most intently to find out if there's planets going around these stars. Are they looking at larger stars or smaller stars to see if they're...
Yes, they are.
So
But
they're happy to find planets around any kind of star.
They are, but what they're discovering is the more sun-like the star, the more likely it is to have planets going around it. If you get too big or too small, the probability drops down. And right now, as we are filming this, astronomers have found little more than 100 planets outside of our solar system. But none of those planets that they've observed so far would be candidates for a life support system. You're typically dealing with, planetary systems where the planets are too big or too small, too close or too far away, or their orbits are too elliptical or not coplanar enough in the case of multiple planetary systems. So we've yet to find an analog to our solar system where a life support planet could possibly exist.
Are they finding any planets going around double stars?
Yes, they have found one.
Okay.
But it's a big planet. Again, it's one of these special orbits where everything is just right to make it possible. It's not the rule, it's the exception.
Now, one of the concerns, of course, is the longevity of the planetary system.
Right.
For life to form on the planet that goes around this sun, that planet has to be there, at least from an evolutionary perspective, for quite a long time.
Right.
That's probably one of the things that's not necessarily true of these systems.
Well, to put it in perspective, only 2% of the stars in our galaxy, by the most optimistic estimates, would have planets. So 98% of the stars would be planet-free. Only 2% would have planets. And of that 2%, the vast majority are orbiting stars that are much younger than the sun. Only rarely do we have them as old as the sun. And then in terms of the placement of those planets, none are like the sun where the planets are orbiting coplanar, low eccentricity, with the right distribution of planetary companions where you could have a possible life support planet. So although planets are not terribly common but do exist, analogs to the solar system are either rare or non-existent. So,
well, it's an ongoing field. I know at JPL they have this major program where they're trying to construct a in-space interferometer. That's where they have multiple, essentially multiple telescopes, maybe as far as a kilometer apart, working in tandem to be able to give you high resolution and high sensitivity to be able to make an image of a planet going around another star. The goal being to
find
see if
Earth-sized
there's
planets.
Earth-sized planets and to see whether those planets have some form of life or have the elements for life.
well, that's a good point because most of the planets that have been found so far are really big planets.
Big
as
Jupiter-type
Jupiter
planets.
or larger. And the new technology will help us to find the smaller planets. Then we can really start putting these fine-tuning models to the test. Welcome to Reasons to Believe, the television program where we explore new reasons, new evidences for Jesus Christ as Creator, Lord, and Savior, and new evidences for the reliability and accuracy of the words of the Bible. And we've been looking at the design of the universe under the theme, the anthropic principle, the concept that the universe has been structured, purposely fine-tuned to provide an environment for human beings, one of the purposes that the universe maintains. But before we get into this, we've really been appreciating the letters and calls and emails that we've been getting, telling us what you think about this show. Criticisms and suggestions and commendations. And as you know, we're trying something different in this series with 3 astronomers talking about a particular subject, 3 specialists all in one discipline. So Dave, you've got a comment that I think would be helpful for viewers to hear about.
Yes, here's another one of the letters that we received from you out there. Here it says, Dear Dr. Ross, we appreciate very much your weekly program, Reasons to Believe. We found the testimony of the panel members to be especially interesting. We appreciate the scholarly way you approach the relationship between science and our Christian faith. Surely, any open-minded person can see that your approach to the Bible is sound and in no way conflicts with science. Thank you for your thoroughness of your work. Sincerely, Elise and Phil. And therefore, they're coming from Melville, Wyoming, I guess that is. So it's another one of those encouraging letters.
Right. But we also appreciate any comments that you might have about this show, and do take the time to thank Jan and Paul Crouch for their generosity in allowing this program to go out over the airwaves. Well, one of the misperceptions that's very common about the universe is that planets like the Earth are a dime a dozen. They're all over the place. And perhaps one of the most famous examples of that is this movie that Carl Sagan put out called Contact. In fact, I think we got a little clip here for our viewers to see.
Yeah, there are 400 billion stars out there, just in our galaxy alone. If only one out of a million of those had planets, all right, and if just one out of a million of those had life, and if just one out of a million of those had intelligent life, there would be literally millions of civilizations out there.
Well, if there wasn't, it'd be an awful waste of space.
Amen.
400 billion in our galaxy alone, and millions of places out there that would have life in it. And, it'd all be such a waste if we're the only ones here. Well, one thing we didn't really discuss when we started this series off is that the very mass of the universe, its size, its dimensions, is a critical factor for whether or not you get even a single planet like Earth. I mean, if you were to start with a universe that was a little more massive than our universe, then the nuclear physics would work in such a way that the elements in the universe would all be heavier than iron, and there'd be no oxygen, no nitrogen, no carbon, no life. On the other hand, if you make the universe a little less massive, all you get is hydrogen and helium, or more likely just hydrogen. And so unless the universe is precisely structured with the mass that we observe, there's no possibility of a planet Earth. So it's not all a waste. It's all there.
That's given the laws of physics that we have.
Right. Given the laws of physics that God
the-
chose to
Right.
govern the universe, it must be exactly the mass that we observe, to within 1 part in 10 to the 60th, 1 part in a trillion, trillion, or you're not even going to get this planet. And to me, what that does is take the whole design argument one step further, that if you really do need 100 billion trillion stars in order to have just one planet Earth, it tells me that the creator of the universe, the designer, thought enough about us, cared enough for us, that he did not consider it too much effort to build a cosmos of 100 billion trillion stars and carefully shape and craft it
Right.
for 14 billion years, so at this brief moment in time we could have a pleasant place in which to live. So it's not just a powerful creator, an intelligent and knowledgeable creator, but a caring and loving creator.
There's many of these characteristics of the Creator that we're able to determine by looking at these characteristics, as this fine-tuning that we see. The very beginning of this series, we talked about the fact that this Creator was a transcendent Creator.
Right.
Excuse me, that he existed outside of the universe. Now we're beginning to see that there are other characteristics that we can learn about this Creator based on this information that we get about his creation.
Well, what I find ironic is that the more that scientists complain about this evidence for a miraculous creator intervening to prepare this planet for us, the more characteristics about that creator we're discovering. In one sense, I can credit Carl Sagan with the fact that we stumbled onto the fact that, hey, it's more than power and creativity and knowledge and intelligence. There's care and love being manifested here. So I think that's another thing that's really a powerful indicator from the study of the universe, is the more we study it, the more that skeptics try to take apart the biblical creation model, the more evidence they're finding for the biblical creation model.
That's right.
And in some ways, you might argue that it's a help that they say, okay, we don't want that to be the case, because then you go in and you test it thoroughly, and you're
Right.
left with what does stand up is a lot more sound as a result.
Right, right. So thank God for the extra testing that takes place through these kinds of
That's
objections.
Right.
Well, let's talk a little bit about the Earth. I mean, we mentioned how we live in a very special kind of galaxy. Special kind of galaxy clusters, special kind of galaxy. Our sun is unique, but the Earth itself has many special qualities to it. And let's just review some of the more obvious characteristics of the Earth. It must be a particular size and type and orbit. We already talked about its composition. We talked a little bit about its location. In fact, I think in our latest Reasons.org website list, there's 202 characteristics that we post. Planet Earth that must be fine-tuned in order for life to exist on our planet. And one of the things that I think you helped us do on our website, Dave, is to actually have different dates from when we come up with these calculations. And the reader is able to see that the list grows more and more numerous as more and more research accumulates.
Yeah, that was one of the interesting characteristics that actually one of our volunteers first made use of, and in emphasizing something that you've called attention to a number of times, is what happens as a function of time in terms of the number of characteristics that show design. Is it decreasing or is it increasing? And that is one of the things that is very clear in the Earth. As we look at the Earth, we find more and more, and you'll find more and more secular books written. I know in the last few years, one that you called attention to a little earlier was this one called Rare Earth, that brings out these design characteristics. And then there was this one written by
this one, the
Anthropic
cosmological principle.
There's that one, and then the one that was written by Michael Denton, that is calling attention to all of the magnificent design characteristics that are present here in this universe and in this.
This one's a cosmic blueprint.
Here's another one, Cosmic Blueprint.
These are
Michael Denton was Nature's Destiny.
Nature's Destiny. That was
Symbiotic Universe.
Look at
These
that.
are all written by non-Christian astronomers.
Non-Christian astronomers in the last, 10 to 15 years at most?
Right. And this, I think, is one of the latest. What if the moon didn't exist? And this gentleman is a lunar expert, but he documents about 24 different design features in the moon that make life possible on the Earth.
That wouldn't
So don't take the moon for granted.
It's not just that romantic thing that you look at there in the evening with your
There'd
wife
be no
or your
romance at all without the moon. But we'll talk about that a little bit later. But the Earth really is a special object, and just like the sun has to be the right size, the Earth has to be the right size. I mean, what if we were to make the Earth a little bit bigger? Like the gas giants, Jupiter, Saturn, Uranus, and Neptune are quite a bit bigger than the Earth. But the problem there is their gravity is strong enough that it retains a lot of stuff that you don't want for life. One of the properties of planets is that the diameter and the mass are structured in such a way that the stronger the gravity, the more gas it retains. And a planet like Mars, which is smaller than the Earth, doesn't have a gravity strong enough to retain a very thick atmosphere. Earth has a gravity a little bit stronger. Uranus and Neptune stronger yet.
Now, when you look at Venus, for instance, which is very close to the size of our Earth, yet it has an atmosphere that is extremely heavy.
Well, I think we're going to
atmosphere.
reserve that for the next episode, Dave. We've got a special program about why Earth has such a special atmosphere.
Okay, very important.
And you're right. Earth is exceptional in that it has a relatively thin atmosphere in spite of its mass. But if you made the Earth a little less massive than what it is, even by a few percent, it wouldn't retain water. water would dissipate to outer space. And of course, water is critical for life.
Critical for life, yeah.
So going with a planet, even the mass of Venus, would be a problem. It's not big enough to retain large amounts of water.
And then there seems to have been evidence that there was a time when water was on Mars.
Right.
I think they've discovered that in recent years.
Right.
And yet it isn't there today.
It's not there today.
Yeah, that's one of the things that's true is that it seems very difficult to make a planet where you can have a water cycle for the duration that the Earth has had it. You can
Right.
get water on planets, but having a water cycle that lasted
remains
for
there
a few
for-
billion years
Yeah.
is quite.
Well, getting a water cycle at all is a difficult situation, even though astronomers now recognize that Mars 4 billion years ago probably had a fair amount of liquid water on it. The evidence tells us there was no water cycle. There was liquid water there, but no water cycle. But your point, I think, is even stronger. Not only is it really difficult to get a water cycle, it's especially difficult to get a long-lasting water cycle. And that's what's unique about the Earth, is it has this very long-lasting water cycle. And the mass or the size of the planet's critical. Its distance relative to the sun is critical. You put, here's my model sun again. If you, this isn't to scale, of course. Maybe a little closer.
Yeah, use the
Even
little
this isn't to scale. You have to recognize that you can take 1.3 million Earths can fit inside the sun.
Okay. that
So
tells
if we
you.
made it to scale, you wouldn't be able to really recognize the
Wouldn't
Earth.
see it. Yeah.
Be a size of a pea or smaller. But the whole point is that if you put the Earth any closer, then the temperature would be too high. Put it any further away, and the temperature would be too low. And to give you an idea how critical this is, if we were to move the Earth just 0.5% farther away than it is right now, the heat coming down on the Earth would now be sufficiently diminished that it would set up a runaway freezing cycle. Because with a little bit less sunlight falling on the Earth, it makes the planet a little bit cooler. Making the planet a little bit cooler causes more snow to fall. The problem with snow is it reflects sunlight very well. It's like a mirror. And so extra snow and ice on planet Earth by itself will cool the planet, which means more snow forms.
Right.
And
it's
so
kind
you
of a
wind up with
runaway.
this runaway where the planet goes frozen. And that will happen if you just move the planet 0.5% farther away.
That finely tuned.
Now, if you move it 0.5% closer, what happens is that little bit of extra heat causes more water to evaporate into the atmosphere, causes more carbon dioxide to be released into the atmosphere, and those are greenhouse gases. And that little extra release of carbon dioxide and water traps more heat, which causes more water to evaporate, more carbon dioxide to be released, and you get a runaway boiling of the
Okay.
water. And so, yeah, the position of
So
the
very finely
planet,
tuned.
very sensitive, 0.5% one way or the other, and you're going to get a problem. Now, some astronomers have speculated, well, what we could do is put the Earth farther away and give it a thicker atmosphere, which would trap more heat. And so instead of having it 93 million miles from the sun, we could put it, say, at 100 million miles from the sun, but just give it a thicker atmosphere. Have it trap more heat, it would keep the temperature the same.
To compensate. Yeah.
Right. Now, I would argue that that would be acceptable if you're trying to sustain bacteria on the planet. But if you're trying to sustain human beings, having that thicker atmosphere poses a problem. Our lungs are designed to work at a certain air pressure. Drop the air pressure a factor of 3 down or push it up a factor of 2 up, and the lungs don't work. And you say, well, couldn't we breathe by some other mechanism than by
Well,
lungs?
or have slightly different design of lungs, I suppose.
Right. Well, this is something we were talking about. Michael Denton, his book Nature's Destiny, he makes the point that those options fail. That lungs are really the most efficient system that you could biologically design to pull oxygen out of the atmosphere and use it to support respiration. You're not going to get a higher efficiency than lungs.
And that involves the pressure as well.
And to make lungs work, they have to operate at a certain pressure. And if the pressure's too high or too low, you have a problem. You can make it work for a few hours, like when people go diving. But for having it to operate for weeks or months or years, that pressure must be carefully tuned.
It seems like we've almost got a well, obviously the analogy we're kind of driving at there is that this is kind of like a machine, that it's well designed, put together a particular way. But if you go into a VCR and let's move this wire here, you do one little thing and it just kind of quits working. It seems like you say, well, maybe we could just do this, and and sometimes we don't have the capability to address a lot of those issues until very recently, and we're finding that those other issues, by doing it that other way, we run into other bigger boundaries that we just assumed would work. So,
well, I think this explains why the list of design features is growing, because what's happening is that astronomers were just looking at things, well, let's just check the distance and see what we get and what it does to the climate. But it took biologists and anthropologists to say, wait a minute, there's an organic factor going on here too. You got to be able to respirate, and this is showing us additional fine-tuning that you wouldn't have discovered unless astronomers started talking to biologists about some of these features. And so as we become more interdisciplinary in this field of the anthropic principle, I would predict that the evidences for design will grow stronger and more parameters will be discovered. In fact, the last 40 years testify to that.
One of the things that's sort of analogous to this is that people have looked at, could we have life other than carbon-based life? Could we use other molecules? I've forgotten, boron or silicon,
and silicon have been raised
things that have similar characteristics or close to carbon, but nothing has the same kind of capability that carbon has to make very complicated molecules.
Especially if you want the molecules to be stable.
That's right.
You can make proteins out of silicon if they're very short proteins, and if you only want them for a few minutes.
Right.
But if you want stable proteins and complex proteins, carbon's the name of the game.
So that puts severe limitations on the adjustments that you could make to this complex life to compensate for maybe higher temperature, higher pressure, lower pressure, varying atmospheric conditions.
Well, everything we're saying in this series on the anthropic principle is based on the assumption we're dealing with carbon-based life. We really don't care whether the creature's got 2 eyes or 1,000 eyes.
That's not the critical
That's
thing.
not the issue. The issue is the chemistry. And the name of the game is it must be carbon-based chemistry. I think it was Dickey who said in 1961, if you want physicists, you've got to make them out of carbon. It's the only way they can be made.
And then, of course, one of the things that you find is that carbon-based life can't exist on gas giants, for instance.
Right.
It has to exist on rocky planets.
Right.
Like
and it can't
Earth.
exist on Mercury. It's got to be a planet like the Earth.
Like the Earth.
Right.
Mercury being, of course, too hot,
And
too
too
close
small.
to the sun, too small.
Too rocky. So, planet just like Earth.
well, it might be a good idea. I know that a lot of press has been made lately about the various planets that have been discovered outside our solar system. Most of them, obviously, gas giants, just due to the technology we can use. But it seems like we've learned at least kind of began to crack the surface on what sort of planets are out there. And at least thus far, like I said, though we can't find Earth-based or Earth-like systems yet, we found that it's not particularly encouraging in some regards for the types of planets that are out there.
One of the more discouraging factors has just been the orbit. I mean, even with our limited technology, we are able to check the orbits of these planets around their stars. And whereas in the case of the solar system, we're dealing with coplanar orbits that are essentially circular, that's not what we've observed with the 100 plus planets we discovered outside the solar system. What we're seeing is that typically the orbits are elliptical rather than circular. And what we mean by elliptical is that they tend to be a lot farther away from the sun at one part in their orbit than they would be at another part.
Close. Kind of like comets are.
Right.
Comets come close to the sun and then very
Yeah,
far
very,
away.
this is what we would call an elliptical orbit, whereas the Earth goes around the sun in a very nearly circular orbit where it maintains roughly the same distance to the sun at all points in its orbit. And we're discovering that's a rare feature in these extrasolar planets. In fact, we have not yet found a planet orbiting an appropriate distance from its star that isn't highly eccentric. You do see circular orbits where the planet's going very close to its star. And there's good reasons for that. The tidal interaction tends to force it into a circular orbit. But when you get out to the distance of Earth and beyond, we're not seeing that. Whereas in the case of our solar system, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all have circular orbits.
Now, the need for a circular orbit is, again, this temperature interaction, tidal interaction effects that...
Yeah, it doesn't do for the Earth to be this close to the Sun in the
At any time in its
summertime
orbit.
and this far away in the wintertime,
Right, it's just
because the temperature differences
too
will be
much differences
too
in
extreme.
temperature.
Right.
And then, of course, the tidal interactions that would occur.
Well, actually,
vary.
one neat feature they've just found, if I can go back to this, notice when you look at planet Earth, that from the north, the northern hemisphere, it's almost all landmass. Whereas if you flip it around to the southern hemisphere, it's almost all water. Well, the way planet Earth is orbiting around the Sun today, this is the era of advanced life, is that the planet is closest to the Sun when in the northern hemisphere it's winter, and it's farthest away from the Sun when in the northern hemisphere it's summer.
Oh, okay.
And so this has the effect of evening out the temperature for the northern latitudes.
For where most of the people are.
And if you look at the way the continents are structured, in terms of what's below the equator, is that as you go below the equator, there's less and less landmass. Notice that Africa is designed in such a way that it goes to a
Shrinks.
point. And even more so, South America. Very little landmass at high southern latitudes. And then you got Antarctica, of course, where people don't live. But in terms of the landmass, almost all of it is in that portion where it gets ameliorated by this difference between summer and winter in terms of the tilt of the rotation axis relative to where the Earth is around the Sun.
Remarkable.
Yeah.
And it's especially important, to have the big gas giants not be in elliptical orbits either, because just the gravitational interactions with the inner planets like Earth, where you need to live, would kick them out of the solar system.
True. Jupiter and Saturn, the two biggest planets in our solar system, have highly circular orbits, and more than that, they're highly stable orbits, which means they do not have the effect of pulling the Earth out of its life support zone. And this, again, is something we're not seeing in the extrasolar planets.
One of the other characteristics that we mentioned earlier was the need for having them in the same plane.
Right.
What consequence of if that's not the case?
Well, let me see if I can model this a little bit. Here we've got the Sun. We've got a diagram right here on the TV screen. But you could have the Earth orbiting about the Sun like this, and another planet, instead of being in the plane, would be up here and coming down like that.
Right.
Well, the effect of having non-coplanar orbits is that these other planets will disturb the
More
orbit.
than they would if they were in the same plane.
Right. Now, another question you could raise is, well, why bother to have other planets? Why not just have the Sun
And a
with-
single
and a
Earth.
single Earth going around
Yeah.
it? Why mess with these other planets? Well, it turns out the other planets really are critical for advanced life being preserved on planet Earth.
You just got some spectacular evidence of that fairly recently with
Well, but the effect of Jupiter and Saturn is that they're much more massive. I mean, Jupiter is more massive than all the other planets combined. And again, to put this in perspective, you can put 1,000 Earths inside Jupiter. So Jupiter is really big. And because of its great mass, it's able to protect the planet from taking hits. And I think we got a video clip of what happened on Jupiter.
in the early 90s, there was a comet that collided with Jupiter, comet Shoemaker-Levy 9, and while each of these fragments are a little bit smaller, if we see any of the impact craters that they make are well over the size of the Earth. So if without Jupiter there, these sort of comets would hit planets in the center solar system like Earth, and that'd be bad. So.
Yeah. Well, what we've seen here, of course, in this particular program is that there are many characteristics of the Earth that are required for it to be a place where we could live. One, of course, is that it can't be a gas giant. Another is that it must orbit the star at the right place, not too closely, not too far away. A third is that it can't have a a non-circular orbit because of the problems that encounters. And of course, fourthly, is that it has to be within a plane rather than outside of the plane because of the interactions
and
that
there
may
are many
occur.
more characteristics that need to be fine-tuned, but catch us next time, and we'll be giving you more evidences for the fine-tuning in the design of the solar system. Welcome to Reasons to Believe, the television program where we explore new reasons to believe in Jesus Christ as Creator, Lord, and Savior, and for the accuracy and reliability of the words of the Bible. And we've been involved in a series of episodes dealing with the anthropic principle. This is a principle that was discovered a couple of decades ago in the physics and astronomy community that is providing us with the most potent evidences for the supernatural design of the universe, our galaxy, and our solar system. And Dave, why don't you just review where we left off in the last episode for the benefit of our viewers?
Yes, Hugh. The last time we were together, we were talking about planets and the discovery of planets around other stars. Been, I think, over 100 of them discovered at this point in time.
We have 107 extrasolar planets.
And so we were talking about those planets and whether there is any chance that those planets could be a planet like the Earth and have the kind of environmental characteristics that would support life. And one of the things that we were discussing was the fact that it's not sufficient just to find a planet that is sort of rocky and like the Earth in that it is near a star in a similar location that the Earth is, but there has to be a suite of planets, very much like our own solar system. And you have to have these planets located in the right places around the Earth, or at certain distances.
There has to be the right number of planetary partners, right sizes, the right distances, right kinds of orbits.
All of those characteristics have to be present there, and we're discovering, of course, more and more why that's important. And these are the design characteristics that we're discovering about our solar system. And what we noted was that the chances of finding another solar system that not only has an Earth-like planet, but has all of this suite of planets in the right places and in the right masses and so on, is really less and less. The chances of finding that kind of thing is very small.
So utterly remote, we can see this as a piece of evidence for the supernatural design of our own planetary system.
Exactly.
Right? So.
Well, and one thing, I was at a American Astronomical Society meeting a year or so ago, and one of the things they were talking about is that while it may be possible to form the solar systems like ours, that it is very hard to get them to last anything more than a few million years. And not only do you need to have the various planets where they are, but they also need to be able to last for a few billion years, or else we're not going to be here.
Right.
So.
Yeah, we're talking about billions of years needing. Rather than millions of years.
Mm-hmm. Well, for example, you got to keep the orbits of the different planets almost perfectly circular. And when you have a suite of planets over the course of millions of years, the dynamics works to destabilize that kind of configuration. So it's interesting that the conference that you're at made note of this.
Right.
So, well, today we thought we would look at the moon. The moon really is remarkably special in many respects. And I remember when I was a graduate student, I don't know whether this happened to you as well. I mean, Jeff, you're a little younger, but back in the 70s, we'd be taking courses in astronomy at the graduate level, and one of the themes was, how did the moon form? And it was actually something I studied when I was a young boy. I mean, I was real interested in how solar systems and planetary systems form, but what I discovered in the 70s, not a whole lot had been achieved since I was a young boy. And I had these 3 up-to-date textbooks at that time on the formation of the moon, and they basically outlined 3 different models
we were
for how the moon could form. And one model was, you have the solar system forming out of this nebula of gas and dust, where you would quickly get a star and then a flattened disk, and then how the disk, through the interaction of gravity and electromagnetic forces, would separate into a series of rings, and each of those rings would form a suite, would form a planet with a bunch of moons going around it. And so one theory was that the Earth and the moon both formed from that primordial disk of gas and dust. But what they quickly discovered is that you can't get a moon the size of our moon, a small planet with a gigantic moon forming out of this flattened disk of gas and dust.
Now, when you say that we can't get it out of a disk like this, what you mean is that the scientists have attempted to model a disk and a collapsing disk and collapsing into planets, and those models are unable to account for a large moon going around
Right.
a planet the
Using
size
the
of the
forces
Earth.
of physics and using what we know
Know
about the
about-
conditions of the early solar system, the best that the models can produce would be 1 or 2 or maybe 3 really tiny
Small
moons.
moons, much
orbiting
like we
around-
find around some of the other planets.
Well, like Mars.
Yeah.
Mars has got a couple of tiny moons orbiting around it. And if you look at all the planets in our solar system, you notice that the planets are much more massive than their moons. Jupiter's got some moons that are the size of our
fairly
moon.
large, yes.
But Jupiter is 1,000 times bigger in terms of its volume. I think about 380 times in its mass, greater than the Earth. So because it's so much bigger than the Earth, when it forms, it can form moons that are the size of our moon. But our moon is exceptional in that it's so large compared to the planet. And the fact that it's a bachelor, you got one moon, one gigantic moon orbiting a relatively small planet.
Yeah.
So that theory doesn't work. And another theory was, maybe the moon got captured.
There was some moon-sized object floating around in the
Well, to kind of give
solar
you a
system.
picture of this, let's assume that this was the Earth. And then you've got a bunch of junk floating around the solar system. There's asteroids and planetesimals in the early solar system. One theory was that here you got the Earth, and some foreign body in the solar system happens to make a close pass by the Earth and gets captured
Somehow gets
to make a
captured.
moon. But the problem with that theory was that the Earth is so close to the Sun. And the dynamics of the Sun and the Earth operating on this capture body leads to one of two scenarios. In fact, there are computer programs you can buy today where you can actually model this for yourself. I've got one that
It's not that complicated.
it's not that complicated of a problem. It's
I've
just
actually seen similar stuff. You can actually get it out on the web and just specify various bodies, and it'll do the simulation
It'll
for
do
you
it
right
for you.
there in real
it'll
time.
do it right for you, and you can actually watch it. What you discover is the laws of physics will lead to one of two scenarios, with the Earth being positioned the way it is from the Sun. Either the Sun will wind up capturing the body, and it won't capture it, it'll actually pull it right in and absorb it. Or the body gets kicked away from the Earth. And so it becomes a free orbiting system around the Sun. But
Right.
the gravity simply won't permit the Earth to capture it into an orbit. It could
Right.
collide, but it's not going to go into a stable orbit.
Right. Given that it's a body that comes in from the outside.
Right,
Having the
right.
dynamics that would be present to bring it into the
Right.
location around the Earth.
And the third thing that I was taught in the 70s is that one possibility could be that something much bigger than this object, for example,
Smashes into
smashes into the Earth like a head-on collision. It actually splits the Earth into a big piece and a small piece. Small piece becomes the moon, the big piece remains the Earth.
the right. In fact,
So-
I think if I recall, they believed that maybe the oceans or some of the continents were formed at that time, and that this big piece came out of the Earth. And
Well, that comes out of noting that planet Earth, you've got this, huge Pacific Ocean basin.
yes,
And so part of the thinking was, if you got this collision event
smashing event,
where it splits into two, maybe the Pacific Ocean is that hole or that,
or left
that
over.
cavity that
Yeah.
was left over from the collision event.
Yeah.
But it turns out that this doesn't work either.
When you try to model these now using the laws of physics,
Right.
it just doesn't. It won't work.
Well, it's really hard to split the Earth into two pieces.
Yeah.
I mean, it's hard to do that to any planet. And if that were to happen, again, given the proximity of the Earth to the Sun, this split-off piece would never become a stable orbiting moon around the Earth. It would fly off. or wind up colliding back into the Earth. So
Just doesn't work that
just
way.
doesn't work, right?
Well, it's kind of interesting too. I mean, you look at that, and that was what we were being taught in the 70s or so, and that's essentially, with minor variations, what I was being taught in the 90s too. So that for better than 20 years there, no real progress was made as we were looking at the general processes that we would kind of know were going on there.
Well,
and the
for
general
that matter, these three theories were prevalent in the late 50s. So it's like all this time had gone by. I remember the textbooks I had in the 70s when I was at the University of Toronto, and one by Berlage made the comment that, there are no other possibilities for forming the moon, and none of these work. And therefore, he said, tongue-in-cheek, the moon must be a miracle.
Miracle. There you go.
So we just can't come up with any physical explanation for the moon.
Well, probably what had happened, though, in that time frame is the tremendous improvement in computers and our ability to actually simulate these kinds of problems on a big major computer. So I think that's probably what's happened
because
in that
back in
time
the
frame.
50s, 60s, and 70s, you had great difficulty coming up with highly detailed models
Correct.
of what the physics would do. But actually, the breakthrough wasn't so much computing power as it was the U.S. taxpayers sending astronauts to the moon. The Apollo program that ran from '69 into the late '70s. And, part of that program was bringing back rocks from the moon. And I remember I wasn't a graduate student any longer. I was at Caltech.
Right.
In fact, we were there together at
Students
Caltech.
together, postdocs.
Postdoctorals together there. And that's when it was announced to the astronomical community that these rocks are giving us unexpected results. And the unexpected results was it was showing that the moon was only slightly younger than the Earth, and that the composition of the rocks was lighter than Earth material.
Okay.
And
lighter meaning
Less dense.
not
less
that they're
dense.
yeah. Okay.
So, the Earth has got all these heavy metals in it, whereas the moon didn't have the quantity of heavy metals that the Earth did. And so why is the Earth a lighter density, and why is it a little bit younger?
The moon, a lighter density.
Than the Earth. And this is what, again, thanks to supercomputers, led to a new analysis of the origin of the moon. And that was a very special kind of collision event. In fact, we have a simulation here to show our folks
Yeah,
here.
maybe we can have a look at that.
This was generated by NASA, a simulation of a collision event that led to the formation of the moon. And so what you see here is that a body about the size of Mars collided with the Earth, not a head-on collision, but not a grazing collision either. And what happened was that the collider was basically absorbed by the Earth, but a debris cloud was sent up away from the gravity of the Earth, and so this fine dust and debris coalesces into the moon that you see over here on the far left. So, and there's been a lot of advance since the early 90s when this theory was first suggested, and it's progressed to the point where astronomers they know fairly well where the collision took place relative to the, just to bring back my little basketball here. The problem with what we were taught in the 70s was that the collider hit the Earth head-on and split the Earth into two pieces.
Right.
What we now realize is that the collider did not hit head-on, but it wasn't a grazing blow either. A grazing blow wouldn't have done that much damage.
And the thing would have probably continued.
It would have just continued off, right. But so it's roughly halfway between grazing and head-on, and the effect of that is that the collider basically gets absorbed into the Earth. But it destabilizes the Earth in such a way that you get a separation of the material, and the Earth being more massive. Now, when we say a Mars-sized collider, we're talking a body that's about 60% the diameter of the Earth. So this isn't a good model.
That's not a good model.
Yeah, it's much bigger than this
that.
wax ball. On the other hand, the mass difference is substantial. Mars is only 1/9 the mass of the Earth.
Because it's proportional to the volume. Yeah.
It's proportional to the volume,
It's the
right?
cubic
So
radius.
it's 1/9 the mass of the Earth. And the mass difference is such that when this collision takes place, with the object hitting halfway between head-on and grazing, that the Earth winds up absorbing all the heavy stuff in the collider. And the light stuff in both the Earth and the collider gets ejected
And ends up in the moon.
and ends up as this cloud of debris around the Earth, which, as we saw in the video clip, over time coalesces to make a moon. And that would explain why the moon would have a lighter density and why it would be a little bit younger.
Now, why would it be a little younger? What is the effect
Well,
that
it's
is
younger.
accounting for that?
It's younger in the sense that the Earth forms with the other planets in the solar system,
Yes.
along with the Sun. And so the Earth comes in at 4.566 billion years, plus or minus 0.002. We got a real accurate measurement of that now. And so we have the Earth already formed. And at a considerably later date, we have this planet colliding with the Earth. And so the early solar system would be more chaotic than the present solar system. And here's this rogue planet that probably got destabilized by Jupiter. It was up around Mars somewhere, and with Jupiter's strong gravity, it could have destabilized the orbit. And this planet winds up colliding with the Earth.
So we're thinking this may have been originally a planet, perhaps
a fully formed planet.
fully formed planet,
fully formed planet.
around the orbit of Mars, you think, or further out, or
Well,
closer in? We don't know
we
exactly.
don't know exactly where it was because it was a planet for whom we can only trace the fact that it was on a collision path with the Earth. And it could have been in a variety of positions relative to Jupiter and Saturn and have been destabilized and sent on this rogue path.
Going back, you asked the question, why does it appear younger? But basically, wouldn't it be that as the colliders happen, when you're measuring the ages, you're measuring back to the last time where it melted.
Right,
And so in that collision, you're going to melt all the stuff on the moon.
right.
And so
Okay.
those rocks are going to be younger than what
Okay.
what was
okay.
on the Earth.
Okay.
And the date that's coming in now is 4.47 billion years ago. So it's like 70, 80 million years after the Earth formed and the other planets formed. This collision takes
Collision
place.
takes place.
Right,
And those ages, I guess, help in deciding exactly when that took place.
right, right.
Now, of course, the interesting thing is, what is the effect of all of this on
Right.
the Earth, and how does this fit into our design parameters for the Earth? Maybe we should say something about that.
Well, this was really a tremendous blessing in terms of preparing the Earth for life. As you look at the solar system planets, one of the things you notice is that the more mass of the planet and the farther away from the sun, the denser the atmosphere. And all this makes sense. So the planet's got more mass,
Sure.
it's got more gravity, it's going to hang on to more atmospheric stuff. And the farther it is away from the sun, the colder it's going to be, and therefore the less gases will volatilize away from
Away
the
and escape from
planet's
the Earth,
atmosphere. And what we notice, for example, is that Mars has quite a thin atmosphere. It's 1/9 the mass of the Earth. Venus, which comes in around, I think, about 85% the mass of the Earth,
Very close.
has an atmosphere 40 times as dense as the Earth. And then you go to Uranus and Neptune, the next biggest planets, and they have a very dense atmosphere. And we call them gas giants because the
Yes.
atmosphere dominates
Well, and
the total mass of the planet.
yes.
And what we discover here is just how sensitive mass is to how dense the atmosphere will be. So it's, even a very small change in mass will mean that the planet accumulates a much denser atmosphere.
So
So-
probably at this time, then, of this collision, there was this very dense atmosphere around the Earth.
Astronomers estimate that the atmosphere of the Earth before the collision was at least 100 times as dense as it is today.
Okay.
And the collision event had the effect of blowing off the primordial atmosphere. So the Earth lost its first atmosphere.
Original.
And then through the process of the collision, the formation of the moon, we have a much thinner atmosphere replacing the primordial atmosphere, probably coming from outgassing within the planet. But that outgassing had already been largely spent, so there wasn't a whole lot more to get.
Well, doesn't it also change the composition of the atmosphere too, so that instead of having carbon dioxide and stuff like that that's prevalent on Venus, we have a much more life-suitable atmosphere?
Right. Yes. So the atmospheric composition would change, and in terms of what kind of atmosphere you get, it's really critical when this collision event takes place. Because if the collision event takes place too late, you won't get enough outgassing from the planet to make an atmosphere that would be suitable for life. But if the collision event takes place too early, then you get too much outgassing and you get an atmosphere that would be too dense for life.
Was there any material change in the Earth's in the material content of the Earth as a result of the moon? Did it bring material into the Earth that wouldn't have been there otherwise?
Well, definitely. I mean, the moon, this Mars-sized collider transferred its heavy elements to the Earth. The light elements went in a debris cloud. So one net effect is that the Earth became extra enriched.
Okay.
In heavy elements.
All right.
And in terms of any body we can see in our solar system, or for that matter anywhere in the galaxy, planet Earth comes in as a heavyweight champion.
Okay.
It's the richest in these heavy elements.
And how is this important for life?
Well, it's important in that we need heavy elements as nutrients. You need some silver in your body and copper and iron and all that. You need it in the right form, which is a whole other story. But the thing that we really need in terms of sustaining life for a long period of time is lots of the heavy radiometric elements. Uranium and thorium are the driving engines of plate tectonics.
Okay, which is another whole story and the importance
earthquakes, volcanoes. I mean, they
all of
happen.
those natural disasters that many people object to actually turn out to be very important for life.
They're very important for life. I mean, the Bible speaks about God building continents. In the third creation day of Genesis 1, let the great land masses form. Well, scientists have now discovered that the tool for that formation would be the plate tectonics and volcanism. And without all the uranium and thorium that the planet would have been extra enriched by thanks to this collision, that wouldn't have happened. And what we see in other bodies in our solar system is you can see evidence for plate tectonics, but it's short-lived. I mean, what Earth has is a long-lived plate tectonic and volcanic activity.
Well, yeah, if I'm correct, there's only one other body in our solar system that we detect any sort of tectonic activity, and that's a moon of either Saturn or Jupiter. One of the two. Of Jupiter.
And that's because of the tidal forces
Right.
that Jupiter interacts that you get that. There's some evidence of past plate tectonic activity, possibly on Mars, but very short-lived.
Right.
And then the other thing is that we have this strong, stable magnetic field. And to get that, you need the planet to really be very rich in nickel and iron, cobalt. These are the ferrous metals that will generate these magnetic fields.
And so these were enriched, as you say, by this collision.
Right.
So it provided an Earth then that was capable of supporting complex life, which wouldn't have been the case otherwise.
That's right. So, yeah, go ahead.
Well, it's just, it kind of seems like, a recurring theme is that not only does this have to happen with the right size body, hitting the right Earth at the right place, moving at the right velocity, but it needs to be at the right time with the right amount of,
well, the collider has to have the right composition to make sure you get the right
enrichments.
And all of this has to be exquisitely fine-tuned, or there'd be no possibility of life, certainly for life existing for a long period of time. And if you want human life, we need a long history of life on the planet previous to us.
Well, and it's interesting too. You look at we were trying to study the moon formation, as we were looking at the general kind of probable scenarios, none of those panned out. Only when we began to look at the very specific, highly improbable scenarios did we find one that seemed to work.
Right.
Again, just an indication that we're looking at a designed event instead of a chance natural event.
Well, I mean, this is even acknowledged by astronomers who are not believers. I mean, there's a book put out by Neil Cummings, for example, and the entire book, it's on the theme, what if the moon didn't exist? And,
I think we have
yeah, we got a clip of it right
clip
here. This is
that
the
shows
book.
that book, yes.
So here's an entire book written where the author, an astrophysicist, just says, well, if the moon were any different, what would happen to the Earth? And what you discover is change the moon ever so slightly in terms of its mass, its characteristics, the collision event, and you discover that there is no possibility for life existing on
Yeah,
Earth.
that was a question, a natural question that arises, of course, is, you know, how fine-tuned is there any way in which this could vary, or you could accomplish some of these things like the exchange of the atmosphere, or you know, the enriching of the Earth? Is there any other way in which these things could happen? And I guess the book is giving us the answer to that.
Well, the remarkable thing, Dave, is that with all this research of figuring out, you know, how the moon got here,
Right.
we're back to where we started.
Well,
it's a miracle.
Yeah, that's the thing that is interesting.
I mean,
here.
the fine-tuning is so remarkable that it forces you to the conclusion that this is not an accident. This is the product of supernatural design.
Your professor's comment there, tongue-in-cheek, turns out to be more true than he probably would have liked.
That's right. That's right.
Yeah.
So,
Well, this is an amazing series of events that took place here.
well, we'll wrap this up next time. There's a little bit more we can say about the moon, and then we'll move on with our theme on the anthropic principle. But this really is a fertile field for the strong evidences for supernatural design. Join us next time. Welcome to Reasons to Believe, the television program where we explore new reasons to believe in Christ as Creator, Lord, and Savior, and for the accuracy and the reliability of the words of the Bible. And a theme we've been examining these past few episodes is something that we astronomers call the anthropic principle. And when we look at the universe and our galaxy and our solar system, we see that it has fine-tuning that indicates that the cosmos, our galaxy and our solar system, were in some respect designed for the support of life and human life in particular, hence the anthropic principle. And we've been moving from the universe to our cluster of galaxies, to our galaxy, looking at the planetary system in which we reside. Last episode we examined the moon and the characteristics that it has. Today we want to look at what's special about planet Earth that points to a supernatural designer. I do want to tell all of you that we really appreciate the letters that we've been getting from you, suggestions, and we encourage you to keep doing that. It really helps us in designing new programs and new themes for future television viewing. And so any criticism, comments, suggestions you have, we'd really appreciate hearing that from you. And the address you'll see at the end of the show. Last time as we were talking about the moon and you know, how the moon really is a miracle, and the way that it's been structured and designed so that life would be possible on the Earth. And we really focused a lot on how the moon formed and how the formation of the moon transformed the Earth so that the Earth could support life, how it wound up with a thin atmosphere to replace its primordial thick atmosphere, and how it got the right composition, the right mass that would make life supportable. But one thing the moon does today is that it helps stabilize our rotation axis. And if we could just go back to the event, and let me pull this basketball. We don't have our planet Earth. We forgot to bring it, but you know, this represents the Earth, and we have the collision event. It was a Mars-sized body that hit the Earth. Debris cloud formed. Out of the debris cloud, the moon formed, and then the moon began to spiral slowly away from the Earth. Now, as the moon spirals away from the Earth, its gravitational pull on the Earth changes. And the moon plays a critical role in breaking the rotation rate. So as it moves away from the Earth, the rotation rate of planet Earth slows down. And
Originally, it was somewhere around a quarter of a day, I think.
yeah, we're talking
4
at the
times
formation of the moon that it was about 4 hours a day. So it's about 6 times faster.
6 times faster.
Right,
Okay.
and then the current. So the Earth was a very fast rotating body. And there's some speculation that maybe the collision event itself may have spun it up a little bit. But yeah, we have good evidence that it was rotating much more rapidly early. But thanks to the moon's gravity, that rotation rate gradually slows down. And I think you can see the physics here with the moon out here. The moon is going to exert a stronger gravitational pull on the near side of the Earth than it does the far side of the Earth. And the difference in those gravitational pulls acts as a rotational brake. And that's going on to this day. I mean, even now the Earth is rotating more and more slowly because of the gravitational interaction with the moon. The sun has a smaller contribution.
Well, that's also what gives rise to the tides.
Gives rise to the tides, right.
Which is a very important thing for
Well, the tides are
life.
important for life, in that
Right.
if you've got continents and oceans, you can amplify the tidal effect. And what this does is it brings in nutrients into the coastlands and also removes the garbage. And so the tides play a critical role in increasing the biodiversity and the biomass of the planet, which allows the Creator to bring human beings on the scene a little more quickly, and then we get to have more bioresources into the crust of the Earth thanks to these tides. And as the moon continues to spiral away, I mean, the Earth will continue to slow down its rotation rate. But I'd argue it's no accident that the Creator places human beings on planet Earth when you've got a 24-hour rotation rate. That's what's ideal for human beings that are going to develop civilization. If the rotation rate's slightly faster, you get more tornadoes and hurricanes. If it's slightly slower, then you get a greater difference in daytime versus nighttime temperatures. So what we see is the ideal, 24 hours a day. But the other thing the moon does for us is, because we have this moon located 250,000 miles away from the Earth at the present time, and because it's so massive compared to the moon, it acts as a stabilizer on the tilt of the Earth's rotation axis. So we have the planet rotating 23.5 degrees relative to the solar plane, but because of the moon, our planet stays at that 23.5 degrees. Now, if you look at the other solar system bodies, you discover that the rotation axes are flipping around like this. Now, that would have a disastrous effect on the Earth's climates if our rotation axis were flipping around like
Now,
that.
the period of time that this flipping around occurs is a very long period of time. For
Over
these other-
hundreds of millions of years.
Right.
But it's such...
Now, that's separate from the idea of the precession.
Right.
Yeah, okay. There is a precession, of course.
kind of like the spinning top where it
there's
does this.
Yeah,
Right.
of course it's very much smaller than what you indicated there, but
26,000 years.
yeah, but it's over a 26,000 year period.
Right.
Yeah.
So
So not only is it miraculous that we have a moon in the first place, but it actually provides, or the impactor event does a lot to make Earth habitable. But the fact that we have a moon as large as it is now is also very important.
Extremely
it's also very
important.
important, right?
You can't just have the event and then have things.
It's important we have only one moon, and it's important that it be really big. It's important that it be a certain distance away from the Earth, and that gives you the maximum stability and rotation axis. I mean, if you're a bacterium living 3 billion years ago, you can tolerate fairly
lot.
wide swings in the tilt of the rotation axis. But if you're talking horses, cows, and whales and human beings, you need that rotation axis to remain stable.
Now, there's a number of different characteristics about the Earth that we would like to discuss today that are important for complex life to be able to exist on the Earth.
Well, just like last time we mentioned a book. That,
Yeah, maybe we could mention that book that...
Well, this is a book put out by a paleontologist and an astronomer. The astronomer is an agnostic. The paleontologist is an atheist. We actually interviewed Don Brownlee on our webcast at reasons.org. We had him on the show for a couple of hours talking about this book that he wrote, and it's called Rare Earth. And what I find remarkable about the book is it's got a theme that's virtually identical to what you see in the book I put out, The Creator of the Cosmos. That when we examine the Earth, we see it has these huge number of very finely tuned characteristics that makes life possible on the Earth. And so here's this atheist and an agnostic drawing the conclusion that Earth is rare in the universe in its capacity to support life. It may be the only one.
This is in sharp contrast to the story that we heard here. It's been probably Carl Sagan did his Cosmos series, 20 years ago now? Is
Right.
it that long ago?
Almost 30 days.
30, is it right? 30 years ago, where he was indicating that there were probably millions of planets very much like the Earth supporting life within our own galaxy, let alone other galaxies.
Well, the difference there, Dave, and I took a course once from Carl Sagan when I was at the University of Toronto, and he talked about this in his lecture series, where he said, well, we really don't know how many planets in the universe can support life, and since we don't know, let's assume that it's 10%. Well, what's happened, and this is what's brought out in this book, Rare Earth, is that we don't have to guess what these probabilities are anymore. We know enough about our planet and other planets and these extrasolar planets to be able to put real probabilities, at least better probabilities, on what it would take for a planet to support life. And it's no longer 1 chance in 10, it's more like 1 chance in 10 to the 217.
When you
So,
take into account
when
all
you
of
take
the...
into account everything.
Now, what are some of these parameters that we would like to, or are important?
Well,
for
one
the
obvious parameter is mass. I mean, the mass of the planet will determine, for example, what kind of ocean you have, what kind of atmosphere you'll have.
I think we have a visual here
Yeah,
that
we
shows
do.
a few different sized planets within our own solar system.
What you see here is Mars on the left, Earth in the middle, and Uranus. And we picked these three because, pardon me, is that Venus? That's Venus. Yeah, it's Venus, which is 85% of the mass of the Earth. Uranus, which I think comes in at about 11 times the
Yeah, that
mass
sounds about right.
of the Earth. And so in our own solar system, these are the two planets that come closest to the Earth in terms of being a little bit smaller or a little bit bigger. And what you notice is just how different these planets are. And you might say, well, Uranus is so much bigger. On the other hand, we need to realize that if it wasn't for that collision event, Earth would have this huge atmosphere which would make life impossible. There'd be this greenhouse effect that would make the surface of our planet scorchingly hot, and the life would be impossible. And in terms of that collision event that led to the formation of the moon, it did contribute a little bit to the mass of the Earth. Because if you look at Venus, roughly 85% of the mass of the Earth, if that were positioned where the Earth is, we would discover that that planet would not be able to retain water over the period of time in which life has existed
Just
on the
because
Earth.
its mass is just slightly smaller than that of the Earth.
Right. I mean, our planet Earth has just enough mass to retain water over a significant period of time. And actually, our planet does lose water to outer space. Its gravity is not quite strong enough to hold on to it totally. But we get enough water coming in, small supply from comets, that it balances the amount of water that we
That's
lose.
being lost.
And so we do experience a tiny loss, but it's such that our planet can sustain large liquid water oceans over the course of 4 billion years. Whereas if it was slightly less massive, we're talking only 1% or 2, that wouldn't be the case. But if you make it slightly more massive, then you wind up with a situation like Uranus, where it starts retaining stuff you don't want it to
You don't
retain.
want to keep.
So,
Can you put any number? I mean, how much more massive would it have to be before that becomes a problem?
well, in terms of just the pure gravity problem, I mean, water's got a molecular weight of 18. Ammonia has a molecular weight of 17. Methane of 16. And so, if you make the planet's gravity a little bit stronger, it now has enough gravity
percent we're
to
talking
retain
about.
not just water, but ammonia. Now, because of where the Earth is positioned, even if it had ammonia, the solar radiation dissociates the ammonia. And so you got photodissociation going on. But again, putting it a little bit more massive would also have the effect that the atmosphere would be a little thicker. When the collision event would take place, you would get more outgassing. And just in terms of our being able to breathe, lungs, which is the one organ that allows for very efficient respiration. In fact, there's a book we have in our catalog written by another agnostic, Nature's Destiny, by Michael Denton, in which he makes the point how critical the air pressure of planet Earth is. And if you make it slightly greater or slightly smaller, then lungs won't work. And if lungs don't work, then you're stuck with animals that have a very low respiration rate, which means they can't do a lot of activity.
So it seems like there's it's not just you change the mass a little bit and you've got gravity, but there's also a number of subsequent consequential factors as well that.
Well,
that
for
we
life
depend
to be possible on our planet, especially advanced life, the air pressure must be just right, and then the composition of the different molecules that make up our atmosphere must be just right. I mean, of all the planets in our solar system, ours is the only one that is nitrogen rich. And in order for respiration to be efficient to allow advanced animals, you need about 20% oxygen, but you need an inert gas to buffer that oxygen. And the only one that's going to work is nitrogen. And so it's
Has the
important.
right molecular weight and so on.
I
to be
mean, you could
retained.
use argon, but if you've got argon, you've got a lot of other things you don't want in the atmosphere. So nitrogen is the name of the game.
Really the right one.
That was one thing I remember, going in 7th, 8th grade science, they talked about how, our atmosphere was only 20% oxygen or so. And I thought, hey, oxygen's so good, you need it for life, you need it to breathe and everything. Why don't we have a lot? And it wasn't until I got older and realized that, it's a very reactive chemical that has a lot of dangerous properties that were it not for the nitrogen to buffer it, you'd have severe problems on the
Cause
Earth,
things
too.
to rest. Our tools
true,
would
too.
get rusty
Well, it
much more
actually
quickly.
causes our bodies to rust. I
Yes.
mean, too much oxygen. I mean, oxygen's toxic to life. And, advanced life is designed to have these antioxidants to buffer the effect of the corrosive nature of
effects
oxygen.
on our cells. And
But push our atmosphere up to 25% oxygen, and that system gets overwhelmed, and you wind up with human beings that would die very quickly. Plus
Now,
the fact if you go up to 25%, you're going to burn everything. I mean, you're going to have grass and forest fires all over the place.
I think we have a visual that shows the 3 different planets
And its atmosphere.
and the atmosphere. Here, maybe you could comment on this. This
Well,
is
now we do have Mars on the scene. That's on the right.
Right.
Venus is on the left. Earth is in the middle. And what we're seeing here relative to Earth is a planet with a denser atmosphere, which is Venus. That's the one that's got the next highest density. And then Mars, which is the closest to us in terms of having less of an atmosphere. But notice the difference. I mean, Venus, it's 40 times as dense. Mars, I'm trying to remember the figure on Mars. I think it's like 1/10 of 1%.
very
very
small.
small,
Yeah. And so what this shows you is that just very small changes in the characteristics of the planet make enormous differences in the atmosphere.
One question that arises: if Venus were at the distance from the Sun that the Earth is, but being smaller, slightly smaller in mass, suppose it had been hit by a moon like ours was, by a collider, and it eliminated this atmosphere like it did the Earth's. Would the Venus be like the Earth then? You mentioned that having a mass slightly smaller than the Earth still would have bad consequences.
Well, one of those consequences would be, with Venus, you would have a less abundance of heavy elements. And I mentioned earlier in our last episode that Earth is the heavyweight champion, having the greatest number of these heavy elements.
Yeah.
And so going with a smaller planet receiving a collision, you're not going to get the heavy element
In the same way.
benefit.
So you're not going to get the tectonic activity as well.
You're not going to
that
get the
you need.
tectonic activity as well as you need. Moreover, the subsequent outgassing would be less. And so you'd probably wind up with an atmosphere that wouldn't be dense enough.
Wasn't dense enough. Okay.
Or you'd have to change the timing of the collision. But changing the timing of the collision is a problem. And if you move earlier into the history, this means that you've got a lot more junk in the solar system. The older the solar system becomes, the more cleared out it becomes of debris and dust. And so we don't want this stuff generating nasty impacts then.
So this mass is a fairly fine-tuned quantity here.
More than fairly. I mean,
Yeah.
I can't imagine changing even by 0.5% without it doing damage to the capacity to support advanced life.
Now, what about oceans? Now, that's a very unusual property, of course, that we have on the Earth.
Well,
How
here
important is
again,
the
we have a
oceans?
little visual here showing a planet that's got a little more water than the Earth. By the way, it's a small one. What we see over there is one of Jupiter's moons.
Europa, is that?
That's the moon Europa. It's not the most water-rich body in the solar system. It's the second most rich. I think Callisto's got like 65% water. And Europa comes in at around 25 to 30% water. Earth comes in, I believe, at like 0.02% water. So it's quite a bit less than the moons that are orbiting around Jupiter. And then you got Mars, where the quantity of water,
It's quite small.
yeah, again, it's like 0.1% of what we see.
The
Well, much less than that.
The ice cap on Mars, I guess, is carbon dioxide.
Yeah,
is
that's
that? Yeah.
Well, there's a little bit of water underneath that carbon dioxide cap that occasionally gets exposed.
Now, there is a claim that there's a lot of water perhaps under the surface of Mars.
Not a lot. Again, Mars is incredibly dry compared to the Earth, whether you look at the ice cap, the surface water, or the interior. And again, it's because Mars would efficiently lose water to outer space over the course of millions of years. In fact, astronomers believe that the late heavy bombardment at 3.8 to 3.9 billion years ago caused virtually all the water on Mars to leave.
Okay.
So very quickly it transformed from a relatively wet, dry planet into one that was very cold and dry. In fact, Fuzz Rana, our staff biochemist, and myself have just put out and it's not out yet, but it's been written, a book on the origin of life, where we talk about what would have happened with water elsewhere in the solar system. And basically what you discover is you either wind up with these super water-rich bodies, like Callisto and Europa, the moons going around Jupiter, or you wind up with exceptionally dry
bodies.
bodies. Earth is the exception. And
Well,
then we have,
and it isn't important to have the continents. We were talking about advanced life that early in the history of the Earth, there's not much in the way of continents, not much in the way of landmass, but there's abundant single-celled animals. But it's important to have the continents so that the ground and the continents can be prepared for advanced life as well.
that's true. There would be no advanced life on planet Earth unless you had a balance between the continental land masses and the water. And without continental land masses existing above the surface of the water, you're not going to have any carbonate-silicate cycle. I won't go into the details of that, but what we're talking about is the fact that the physics of the sun means that the sun gets brighter and brighter as it gets older and older. That's because as more hydrogen is converted into helium, the helium acts as a catalyst to make the nuclear furnace burn hotter. And so with the sun getting brighter and brighter, it's now necessary to sustain life on planet Earth to reduce the greenhouse gases. But that reduction in heat-trapping gases cannot happen unless you have efficient plate tectonics, a strong magnetic field in the crust of the Earth, and oceans in the right proportion relative to continental land masses that exist above the surface of the waters in order to efficiently remove those greenhouse gases and convert them into sand, into carbonates, and through the agency of life into coal, oil, and natural gas. So without the continents being about 30% of the total surface area of the planet at this time, you're not going to be able to sustain life on planet Earth for more than a few million years.
Because you need to have the continents there to live on too.
Well, for us to
various
live on.
various forms of life.
I mean, I'm thinking about dolphins and whales and fish and
Sure.
bacteria. They don't
need the
necess-
continents. Yeah.
But they do need it in the sense that without the continents, there's no mechanism to counterbalance the increase in the solar
to
luminosity.
remove those gases from the atmosphere.
And when Peter Ward and Don Brownlee wrote that book, Rare Earth, that was the thing I think amazed them more than anything else, is how planet Earth has exactly the right amount of water to sustain this carbonate-silicate cycle so that life can remain here on planet Earth.
Remarkable fine-tuning again here.
Well,
isn't it?
they made the comment, you make the oceans a little bit deeper and you're in trouble. Make the oceans a little more shallow, you're in trouble. You need dense water
Right.
to drive this plate tectonic cycle. And if you don't have enough water, you don't get water at the right density and the right temperature at the subduction zones. But make the water depth a little bit greater, and suddenly you don't have enough continental land masses above the surface of the water.
To provide for the silicate cycle here.
You know, one of the things that Don Brownlee, the astronomer, points out in that book is that, you know, I'm amazed that planet Earth has as little water as it does. You know, his expectation is it would have been a water world. And so when you go to Europa, I mean, that is a water
That's the
world.
way it is. Yeah.
Yeah, I mean, and there you're in real trouble in the sense that at best you could sustain primitive bacteria, but only for a brief period of time.
There's one other fine-tuning thing that we should mention here before we end our program, and that's this the poisons that are present and how those poisons got changed.
Well, we talked about how the moon collided with the Earth, and what that did is it super enriched the planet with uranium and thorium.
Well, they're showing some of
Yeah,
the
here's
some
a
of
list
these
of-
poisons that we need.
Well, I call these things vital poisons in the sense that you have to have some of these elements passing through your body. Otherwise, you're not going to be able to build the proteins that you need to sustain advanced life. On the other hand, all of these elements are poisons, and if you have too much of them, and so
Or in the wrong form.
wrong form or too much.
Well, and most of those are heavy metals too. You know, you
Right.
talk about not wanting to have too many heavy metals. So
Well, for example, you need some arsenic in your diet to make sure you can get certain life essential proteins, but you don't want to overdo the arsenic.
That's right.
Too much arsenic will kill you, but no arsenic at all will also kill you. And
So it was bacteria on the Earth, I think, that was used to change these poisons into forms that wouldn't be as seriously damaging to complex life. Is that correct?
over a very long period of time. And I think we'll talk a little bit about this in our next episode,
Okay.
that these vital poisons really are providing us with some of the most remarkable evidences that there's a supernatural creator out there. And it also explains why life history looks the way it does on planet Earth. There's a reason for the 3.8 billion years. There's a reason why bacteria dominated for so long. All this is essential in order to get human life to transform our planet so that we could be here. Another evidence for the supernatural creator. But we'll pick this up next time. Thank you for joining us, and we appreciate any comments you have about this program, and thank you very much. Welcome to Reasons to Believe, the television program where we explore new reasons to believe in Jesus Christ as Creator, Lord, and Savior, and new reasons to believe in the reliability and the accuracy of the words of the Old and New Testament, the Bible. And these last few episodes, we've been focusing on what's called the anthropic principle, how when astronomers and physicists observe the universe and measure the universe, they see that it has dozens of exquisitely fine-tuned characteristics where the fine-tuning must be really remarkable in order to make life possible on Earth or anywhere else in the universe. Anthropic principle, the principle that the universe has been fine-tuned, it's been designed for the support of life. And in our last episode, gentlemen, we were kind of bringing up the topic of these vital poisons. And we talked a lot about how the Earth and the Moon have a history and a structure that super enriches our planet with heavy elements. And in particular, in order for life to be sustained for a long period of time, we need plate tectonics, we need the silicate carbonate cycle, which compensates for the increase in the solar luminosity, which means you must have a planet that has a very high abundance of uranium and thorium, long-lived radiometric elements that will provide the energy source.
The heat necessary
The heat
to keep
necessary.
the tectonics going.
Exactly. And but because of that, we wind up with a suite of other heavy elements, silver and gold and lead and zinc and tin, molybdenum, iron, And these elements we're talking about are what chemists call vital poisons. And if you were to buy a little book on the atomic elements, I think there's even one in our catalog, what you'll notice is that it will talk about the toxicity of different elements. And some elements are always toxic. Other elements are toxic in quantity. But interestingly, there's a list of elements in the atomic chart, about 22 elements that we classify as vital poisons, in the sense that you need some of them.
Trace elements,
you
trace
need
amounts of them.
trace or greater in order to have health and life. But if you get too much, and the example we talked about last time was arsenic, that you need trace amounts of arsenic in your diet, or you're not going to have the certain proteins that are necessary to sustain human life. But even a little bit more than those trace elements will kill you. An example at the other end of the spectrum, I think, would be iron. We actually need a lot amount of iron in our diet to make sure we've got the proper blood supply and the blood properties to sustain life. But you can actually take too much iron. And so people who take these iron supplements should be cautious that you don't want to overload the iron. Not that many of us have to worry about loading up too much iron in our diet, but if you do get too much iron in your diet, it will have deleterious effects.
Now, the exact sort of amounts of these that are present in the earth or present in the environment today was not necessarily the correct amount that was present in the early earth.
Well, I'd
So
say,
there had to
Dave,
be-
the amounts are the same, but the forms
of the
these
same. Okay.
elements are different, and the
Okay.
location is different. And so with this Mars-sized body colliding with the Earth, we wind up with a planet being super enriched with these heavy elements. But the primordial Earth, at the point where life was first created by God on the Earth 3.8 billion years ago, these heavy metals are essentially evenly distributed throughout the planet and mostly in soluble form. But what our Creator does, God creates a suite of sulfate-reducing bacteria. These are specialized species of bacteria, each one specializing on a certain metal. And what these bacteria do is they're living primarily in the oceans, and the oceans you have these heavy metals in soluble form evenly distributed throughout the water. And these bacteria living in the oceans would filter these elements through their bodies, but each bacterial species, like you got zinc reducing sulfate bacteria, and so what these zinc bacteria do is they consume the zinc in soluble form, convert it into insoluble form, and then when the bacterium dies, we have the zinc sulfide, which is insoluble zinc, falling on the floor of the
bottom
ocean. And so you have these locations at the base of the ocean floor where you would have concentrated mats of dead bacteria, sulfate-reducing bacteria. And so here you'd have a location on the Earth where the once soluble zinc is converted into insoluble zinc in concentrated form.
Right.
And so then plate tectonics will move those zinc sulfide bacterial deposits, and they'll become ore deposits on future continental land masses.
So the tectonics is kind of churning the
Well, the
earth.
stuff gets subducted and it forms.
churned and moved up into the continental
Exactly.
shelves and
So-
areas.
I think it's important to point out too is often I've talked with people and you'll say something where you needed to have 3 billion years of this going on or else we wouldn't be here, and the common objection is that's somehow a limitation on God, that God needed to have a certain amount of time. I think it's important to point out that we're not saying that God needed a certain amount of time, but we're discovering what God did
What
to
God
create
did
the
do.
environment
Right.
where we live today.
Right.
Right.
I think good proof that God could have done it differently, as you see in the end of the Bible, a brand new universe, a new creation, different physics, different dimensionality, different time scales. God had his reasons for choosing the physics that he did, for the dimensions of space and time he did. I believe one of the big reasons is that he wanted to create a stage for the efficient conquest of evil. This is the universe for the conquest of evil. The next universe, there is no evil, and therefore we have different physics.
Different physics and different
Right.
things that that determine the environment. This objection is frequently brought up also when you discuss God taking 15 billion years, for instance, or 10 billion years from the time of the Big Bang until the present, the existence of the Earth, and the making of stars and galaxies and all of the various things that we've in fact discussed in earlier programs. And why did God have to take 10 billion years for all of this to take place? And I think, again, the answer is it's not a question of what God could do. He could have just spoken it all into existence instantly, but he didn't choose to do it that way. And what we're discovering is how he in fact did it.
Right, right.
And given the laws of physics, given that he designed the universe the way he did, then it was necessary for these things to work out the way they did over a 10 billion year period, and now over a 4.5 billion year period for the Earth itself.
Well, I think it's important to point out too that God created life according to our measurements 3.8 billion years ago on the planet Earth, and that's really a short period of time, given the fact that today you can have human life. And 3.8 billion years of life before us, really, in my context, is God really hurrying the whole thing along. Because what we notice is that he creates these bacterial species all at once. He doesn't create the zinc sulfide reducing bacteria first, then later produce the tin ones, and then the molybdenum ones, and then the iron ones. Rather, we see him creating all these bacterial species right away, and he creates them in the maximum abundance with the maximum diversity in order to speed up the process of converting these vital elements into the right form from soluble to insoluble, and then concentrating them so there'd be large portions of the planet where we wouldn't have in concentrated lead that would wind up...
That would cause poisoning of
Well, for
life.
example, even if the lead is in insoluble form, if you have like a human village right next to a lead ore, the lead in the land right beside your village
is enough to poison
you.
Yeah.
Right.
Arsenic, the same thing. You don't want to be living next to an arsenic ore deposit. But the fact is that thanks to these bacteria, there's only a few places on the Earth where these things would be in concentrated form. The rest of the planet, they're hardly existent at all.
Relatively free.
Give you an example. If zinc were distributed like it was before God created the zinc sulfide reducing bacteria, almost everywhere on planet Earth, you'd have 1 part per million zinc in the environment. And that would kill all advanced life. But because of these bacterial species existing for a couple of billion years, it's now been reduced to 1 part per billion. 1 part per billion is the right amount for advanced life. There's enough zinc there at 1 part per billion that it will prevent you from getting sick all the time. Some of us take zinc tablets to guard, because it's a factor in your immune system.
It's an important thing, but not at a concentration.
But you don't want a whole lot of it. I mean,
exactly.
Don't take too much zinc.
Well, I think that's the whole point of this series, is talking about the anthropic principle, that things appear to be designed. Again, it's not just that. That what it appears is that there is some bigger purpose than solely life being here. But given these other constraints, life appears as fast as it is capable of doing, and that's not going to happen unless if you have a design system.
Right, and everything is just right. Not too much, not too little. And it's not just for our benefit. I think of molybdenum. Molybdenum is a vital poison. You don't want too much or it'll kill you. You need enough so that you get the nutrients you need. On the other hand, molybdenum is also a catalyst for nitrogen fixation in the soil. So it's a benefit to other life forms as well. And God designed molybdenum in such a way that you could have the just right amount for humans and the just right amount for nitrogen fixation in the soil. Right. So it takes careful design of the whole elemental chart. So all the physics fits into this.
Now, I know today we wanted to talk about some of the explanations that are offered, these various forms of the anthropic principle that are presented by different scientists and those who are trying to explain all of this fine-tuning, all of this just right
Well, I think it's
adjustments.
fair to say, Dave and Jeff, that all physicists and astronomers accept that there is an anthropic principle, but they don't all agree what form that anthropic principle takes. And the one we've been talking about in these last several episodes would probably go under the title of what's called the weak anthropic principle, which is simply the observation that as we examine the universe and the physics that governs the universe, we see it has fine-tuned properties that make life possible. But there are other anthropic principles that physicists, philosophers, and
Well, what I've kind of noticed is that this term, anthropic principle, is sort of used in two different ways. What you've called attention to and the way we've been using it is it's a acknowledgement of this fine-tuning. It's kind of a single phrase or two words, anthropic principle, to kind of describe the fact that we are discovering all of this fine-tuning in the universe, in the environment, in life in general.
And I think it's fair to add, Dave, that it's not just fine-tuning that our peers are talking about. They actually admit that this fine-tuning points to design.
But then the words are also used in papers and in the scientific community to refer to an attempt to explain this fine-tuning. And that's where you get these different kinds of anthropic principles, different explanations, which they also attach the word anthropic principle to.
Well, for example, Paul Davies wrote a book back in 1986, I believe, called The Cosmic Blueprint, in which he concluded that there was overwhelming evidence for design.
Yes,
But Davies is not a Christian.
correct.
And although a lot of our peers in physics and astronomy, in fact, I don't know of anyone who's done research in this discipline that wouldn't agree with Paul Davies, that we measure the universe and our solar system and galaxy, we are seeing this overwhelming evidence for design, and it gets more overwhelming the more we study the
As time
universe
goes
and the
on.
galaxy.
Now, this weak anthropic principle that you mentioned as one of the ones that is used, when you use it as an explanation rather than the term being used as just a description, the explanation or the explanatory idea here is that, of course, we see this design because if we didn't see it, we wouldn't be here to observe it.
Right.
That's kind of the key thought here. I think we have the overhead here, which is showing that we're here
Right.
because the environment allows for us to be here.
Right.
And if it wasn't fine-tuned that way, we wouldn't be here to observe that it's fine-tuned.
Right.
So that's kind of an attempt then to explain why we see things the way we see them.
And most of our peers really don't try to get at the cause of this weak anthropic principle. They just simply note that, well, of course, we look at the universe, it has these characteristics, we wouldn't be here otherwise. But then there are those that really try to dig a little bit into what's responsible for this design, this fine-tuning.
By the way, I'm quite surprised at how quickly people are willing to accept that as an explanation. The fact, I've talked to scientists at the Jet Propulsion Laboratory, and they feel perfectly content with that being the explanation for why we see the fine-tuning.
Yeah.
They don't seem to be motivated to go a little bit deeper and find out, well, does this really explain why it's fine-tuned so that we can be here to observe it?
Well, fundamentally, it's not an explanation.
No, it's not. It's
simply
more
an
an observation.
right.
That's exactly.
Yeah, it's I think somebody likened it to a guy before a firing squad. That he's out there and if he's there to talk about it afterwards, it's well, of course they missed, or else I wouldn't be here. But it doesn't explain why they missed, or it gives no context for that. it may be a statement that it did happen or something, but it doesn't give any
Well,
explanation for
A
it.
number of philosophers have pointed out it's a vacuous statement in that
Yeah.
it makes no comment at all on what's the cause. But you're right, a number of physicists think it does.
Yeah, they're perfectly happy. Some very bright guys that I've discussed this with at JPL.
Well, that's why our colleague on our staff, Ken Samples, our staff philosopher, says, these physicists need to take a class in philosophy. So
And we
he
have some
realizes-
other explanations here. Why don't we mention them? There's this one called the strong anthropic principle.
Well, this is the argument that the universe has these characteristics because nature requires life to be here. It's this idea that somehow the physics of the universe is structured in such a way that life is intrinsic to the physics. And so it's like the universe must take on these characteristics, not simply the observation that it does. It's one step further saying, well, it's stronger than that. The universe must take on these characteristics because somehow life is intrinsic to the physics, but there's no attempt to identify how or why life would be intrinsic to the physics.
Now, is this connected to the idea that there is some law of physics that maybe we haven't discovered yet?
Some suggest that, some prefer not even to think about it. I mean, it's kind of a little bit like the weak anthropic principle response where they say, well, we're here, of course. We wouldn't be here unless the universe had its characteristics, and I don't want to think about why we're here.
Right.
Or what purpose we might have. Well, likewise, a number of astronomers and physicists and philosophers who argue for the strong anthropic principle only take it to the next step. They say, well, it must take on these characteristics, but they don't ask themselves the question why, and a lot of them don't want to ask that question.
It's almost mystical or certainly metaphysical in a sense.
Well, they don't want to go into the metaphysical territory. I think as you realize, both of you, that a number of our peers want to see themselves as being totally scientific and objective. We never think about philosophy, theology, so these are areas we simply don't want to go. But ultimately, everybody begins to ask those questions. I mean, you're human. I think if you're a human being, that's going to happen.
Very interesting. Well, then we have the third one here. This is the PAP.
The participatory anthropic principle. And this makes the point, it's kind of a Hindu concept, that there's some kind of connection between the observers and the material of the universe. That the very idea of us observing the universe somehow brings the universe into existence. So it's like the universe creates us, but we create the universe.
Create the universe.
Wasn't that also somewhat tied to some of the quantum mechanics principles, that what you observe determines the state of the system you were observing, and so that in that way, and that us observing the universe a particular way somehow drives
we're
it
somehow
that way.
interfering with the universe in a way that causes us to be coming into existence.
Well, the proponents of PAP all admit that this is an outflow of Niels Bohr's Copenhagen interpretation of quantum mechanics.
Okay.
And even to this day, that's probably the dominant interpretation of quantum mechanics. Niels Bohr was such a giant in the early discipline of quantum mechanics that he's cast a rather long shadow over the whole physics of quantum mechanics. And a number of physicists don't realize that Niels Bohr was a Hindu, and a lot of his Hindu philosophy creeps into the physics. And I've got a number of books on my shelf which do a good job at separating the physics of quantum mechanics from the philosophy of quantum mechanics, and how there's, I can think of 12 different philosophical interpretations of quantum mechanics, running the gamut from a realist interpretation to a pantheistic interpretation to completely mystical interpretations of quantum mechanics. But participatory anthropic principle is really founded on the idea that the very act of observing somehow has a factor in the cause and effect of quantum mechanics. And then there are physicists who simply say, well, maybe this extends to the entire universe. Maybe the universe is somehow a quantum event, in which case observers may be intimately tied to the existence of the universe.
Well, it sort of seems to beg the question, though. It's like, we're here observing the universe, but how could we have brought the universe in if we weren't here in the first? It seems to me
strange.
you've got to get it started at some point, and if neither the universe nor the observers were there at some point in time, how it got started, it seems to run into that roadblock at some point in time if you take it backwards.
You're right. It's a very serious roadblock in that,
Violates cause and effect here, in a sense.
well, it violates the concept of time and cause and effect. And if you're going to do that, then there's no science at all. You'd have to argue that the entire universe is an illusion. It's not real. Time, the arrow of time really does go forward. The participatory anthropic principle would have to argue that there's some way that we human beings have the power to reverse the arrow of time. Because after all, we show up on the scene 13.7 billion years after all this quantum mechanics and gravity and electromagnetism and matter and energy show up. So how could we be responsible for bringing the universe into existence if we don't show up until 13.7 billion years later?
Wasn't that kind of the extension into the final anthropic principle there, that
here's
not
this,
only do you just participate,
This
but
fourth one now. This is the final anthropic principle, FAP.
Well, people who promote the
Here
final...
we have it up on the
Right.
screen here.
Yeah, and this was kind of the theme of probably the most popular book, at least amongst physics community, on the anthropic principle, a book called The Cosmological Anthropic Principle, written by Frank Tipler and John Barrow. And this FAP theory is really more attributed to Frank Tipler than John Barrow. And Tipler admits that we have a real problem with the participatory anthropic principle, in that it would require that human beings can reverse the arrow of time. I've often made the joke that if the PAP people are right, the Southerners should be able to reverse the course of the Civil War. All you got to do is have a little meditation meeting and change the whole result of what happened in the past. So Frank Tipler admits that, but he says what's really happening is that we look at the history of life on planet Earth, and we see there's a progression towards advancement and improvement. Now, he understands that there must be something in the record of nature itself that explains this improvement. Not God, but there's something in the physics that would explain this advancement and improvement. And he says perhaps that's happening with the universe as a whole, that life is evolving and improving, and the universe is evolving and improving. And if we just extrapolate that out into the future, there will come a point when all life and all nature, all of physics, would meet together at what he calls the omega point, where they become so improved and so advanced that all of nature and all of life joins together to become God.
Okay.
And
The
God would
creator.
have the power to reverse the arrow of time,
Time and
that would explain where the universe came from and where all life came from. Which generated an interesting comment from the New York Times author and skeptic Martin Gardner. And he says this isn't the FAP theory, he says this is the CRAP theory, the completely ridiculous anthropic principle. Because now we're trying to attribute properties to nature and humanity and life that we can prove we do not possess.
Yeah.
And this whole idea that we're advancing is also something that could be called into question. I mean, from a theistic perspective, the advancement's attributed to God. And we look at the record of nature, Frank Tipler is not right. We don't see this progressive advancement in nature. Rather, we see entropy. Things are running downhill towards disorder.
Deteriorating, yeah.
The only reason we see a reversal of that in life is that we have a supernatural creator imposing this additional design and advancement.
In a way, as we've gone through all of these, what you kind of see is that in the end, scientists really can't explain all of this fine-tuning, all of this apparent design through a naturalistic worldview. And so they're grasping here for what in the end seem to be ridiculous explanations in order to try and explain
Well,
what
this
we
has been
see.
going on for 30 years, Dave, and I think what's happened at the beginning of the 21st century is a recognition that PAP, FAP, and SAP simply don't work. We're basically back to WAP. These other explanations can be demonstrated to be absurd. And so really the whole focus now is, what do we do about the weak anthropic principle? Does it point to a supernatural creator, or are there alternate explanations for this design that we see?
Right.
We'll pick this up next time. Welcome to Reasons to Believe, the television program where we explore new reasons to believe in Jesus Christ as Creator, Lord, and Savior, and for the accuracy and the reliability of the words of the Bible. And on that theme, we've been examining these past few episodes what physicists and astronomers call the anthropic principle. How we measure the universe and the physics that undergirds the universe, we see that it has a number of characteristics, actually hundreds of characteristics, that reveal exquisite fine-tuning. Fine-tuning at such a high degree of level, it points to a supernatural creator. And just to try to summarize, and incidentally, we really do appreciate the comments. We've been getting really good feedback on this series of programs, but we're also looking for suggestions from you for future themes and episodes. So we really do want to encourage you to send in your criticisms, your suggestions, your comments on the Reasons to Believe program. So let us know what you think. You can send email or mail. There's an address at the end of the show. But just to kind of summarize, gentlemen, what we've done in these past 9 episodes is to look at each part of the astronomical and physics record and see the fine-tuning that exists there. We talked about the fine-tuning that's in the universe. 48 different characteristics of the universe where we see this fine-tuning. We looked at our cluster of galaxies. You have to live in the right kind of cluster of galaxies. We looked at our own galaxy. We looked at our planetary system, our star and the suite of planets, the planet itself, the moon. We looked at the chemistry of the Earth itself and how it points to this design. And this has been a marvelous tool for Christians to argue for the God of the Bible, in the sense that it gives us a testable model, in that if we're right about God of the Bible being the answer for why the universe has all this fine-tuning and design in it, then the more we measure the universe, the more we measure our solar system and our Earth, the more evidence we'll uncover for even greater design. The fine-tuning we would predict would get greater rather than smaller, and the number of characteristics showing this design we would expect to increase with time rather than decrease. Not that there won't be places where we misunderstand what we're interpreting. I mean, one example I can think of is that when I was a graduate student, it was felt that only 1 star out of 3 was a bachelor star. We're now thinking that really it's 2 stars out of 3 that are bachelor stars, because now we know a lot more about nearby stars. Although stars like the sun may not be 1 out of 3 or 2 out of 3 that are bachelors. It could be a different number. So small changes like that will take place. But it has been interesting that over the past 30, 40 years now, it was 40 years ago, that the anthropic principle was first discovered, 42 years. And since that discovery in 1961, we've seen that the evidence for fine-tuning and design has been getting progressively stronger and stronger.
This is typical, by the way, in the scientific community, where someone will propose some explanation, some theory, and if the evidence continues to grow, he won't necessarily have immediately all the evidence that's necessary to convince everyone that this is a correct theory. But as time goes on, if it's a correct theory, we expect, and we in fact have the evidence increasing to support this theory. Or if the evidence doesn't increase, and in fact maybe it even decreases, then that theory goes out of vogue. So it's a common procedure that takes place.
So if the atheists are right, the evidence will get weaker with time, but if we're right, the evidence will get stronger.
Exactly.
And one reason we've focused 9 episodes on this theme of the anthropic principle is that this is an arena where the scientific evidence is rapidly accumulating. In fact, one thing you'll notice on our reasons.org website is about every 6 months we update the list of fine-tuned characteristics. I've got a printout, for example, of one item we have on our website, the probability of finding a life support body, whether it be a planet or a moon. And we have up on our website there our calculations about every 6 months over the past 3 years. And so you can see the track record of what's happened over the past 3
Growing,
years.
continuously growing.
And what you notice is that we're adding about a dozen to 20 characteristics every 6 months. And very conservatively, the evidence gets about 1 billion times stronger every 6 months. So within 6 months, you have the opportunity to put to the test whether the non-theistic model, the non-Christian model for this anthropic principle is correct, or rather the Christian model is correct. So you get to test, are the non-theists right, or are the Christians right on this? And what I like to share with skeptics, wait 90 days and we can see who's right and who's wrong.
Yeah.
I'm making a prediction here.
Yeah. Well, and I think what's interesting about that too, and I think is missed, is often in the Christian community we've been criticized for, well, we don't understand this, so therefore it must be God. And
Right.
this is different in that these are things that the better we understand, the more remarkable, or the more remarkable and miraculous they seem. It's not we're arguing we just don't understand it, so therefore it must be
Right.
God. But this is stuff as we've understood and as our understanding has increased, it seemed more miraculous. That it's a very different argument than.
It's
It
kind of
is.
like the moon thing we were talking about here in a previous episode. When we finally did figure out how the moon formed and the effects it had on the earth, it became more of a miracle than previously.
Yeah,
when we didn't
previously they
understand
said, well, it must be a miracle because we don't understand it. Now that we
Right.
do understand it, it's even more of a miracle.
More of a miracle.
Right.
That's exactly right.
So, and this is really what we're trying to promote in Reasons to Believe, is that the way to really advance a theological position is to make predictions. Predict what scientists will discover in the future, and make short-range predictions as well as long-range predictions. If your predictions come true, you've got a good model. It's a model that's worth improving. And that perhaps is appropriate to emphasize. In science, no model is ever perfect because we don't know everything.
It's always fine-tuning that has to take
Right.
place in the model.
But good models are models that are getting better and better as time goes by, whereas
Small
bad
changes.
models get worse and worse.
Right.
And so we can test different theological perspectives. Is it atheistic, deistic, theistic? Is it Christian? Is it Hindu? Is it Buddhist? Is it Islamic? Each of these interpretations of this fine-tuning can be put to the test. Each model would make distinct predictions relative to the other models. And so
Now,
through these predictions, we can tell.
What are some of the responses that we get from various people, scientific community or elsewhere, for this fine-tuning? What are some of the responses that people give?
Well, interestingly, all the responses to this evidence for fine-tuning in design really are not scientific rebuttals. They're philosophical rebuttals.
Yeah.
And, we joke with our philosopher staff member, Ken Samples, that the only value that philosophers serve in society is to help you win arguments against other philosophers. But, that's a critically important task.
It is.
Because often people don't realize when they're preaching philosophy rather than science or history. But perhaps the most common objection that we all hear is what's called the multiverse interpretation. In fact, just days before this recording, Scientific American came up with a major article on the multiverse hypothesis, only they didn't call it a hypothesis. They simply said it's an established fact that there are an infinite number of universes out there. It's remarkable for me to read that in Scientific American because the theory of general relativity tells us that if you've got more than one universe, once you've got observers in universe A, the space-time, say this was a universe, and this is a space-time envelope in that universe. Once you've got observers in universe A, the space-time envelope of that universe can never overlap the space-time envelope of any other possibly existing universe. So I count it audacious that anyone would say the multiverse theory is an established fact. More appropriate, I think, would be to make the statement, well, if there is no God, if there is no supernatural creator beyond the space-time envelope of the universe,
That's responsible for
for
creating, bringing
responsible
this
for all
into
this
a-
design that we
Right.
see, then there must be an infinite number of universes.
Yeah, the idea here being that you have an infinite number of universes that have different laws of physics, different parameters,
characteristics.
and that among those large number or infinite number of universes, there is surely to be one that has all the right parameters for the existence of life, and that's the one that we happen to live in.
Right.
And that's what our visual is showing there. That we've got an infinite number of universes, so ours appears designed. There's a bunch of them out there, so we just happen to live in that one that allows us to be here, basically.
It only works, though, if the infinite number of universes all have different physical characteristics. So if
Right.
they're
Yeah, that's
identical, then it doesn't buy anything.
Correct.
But I think it's important to point out that this multiverse hypothesis is simply a reaction to God as the explanation. If there is no God, then how are we going to explain this design? And they say, well, let's just presume there's an infinite number of universes. They all have different physical characteristics. The laws of probability would tell us if they are truly infinite, then one of them must have these characteristics that would support life.
One thing that I remember, I was in high school about the time Stephen Jay Gould proposed this punctuated equilibrium theory, and was talking with my dad about it. And one of the things he mentioned is he said, it's kind of interesting how more and more the naturalistic explanations look like the creation account. They may attribute different mechanisms to it, but the explanation or the progression of events looks very similar to the creation account. And you look at this here, and it's easy to say, well, that's just it's a good naturalistic explanation. But in reality, what you're appealing to is something outside of our universe is responsible for our universe. Now, they may call it another set of laws of physics, but you could just as easily call it God, and there's no physical difference between the two.
There's no distinction.
Yeah.
They can't distinguish between the two.
Right.
Well, what I like about your dad's comment, it's another way to put to the test the Christian creation model versus all other models. If we see the other models progressively looking more and more like the Christian model as time goes by, isn't that evidence that the Christian model must be the right model?
Right.
So that's, you'll have to thank your dad for that insight.
Yeah.
That was great.
Now, I know that those who have attempted to explain the Big Bang, the inflationary model, the physics that goes on at the beginning of our universe, are claiming that sort of present in the models that they're using is the notion somehow, and in what way I don't fully understand, that they have within the model somehow the possibility of other universes coming into existence, or this model allows for that possibility. Is there any comment that you could make on that, Hugh?
Well, you're right that these multiverse models that are being developed by physicists, what they're saying is if there's really an infinite number of universes, then what's the physical mechanism? And what they all appeal to is what's called a quantum space-time foam. And so you have this space-time continuum which is fluctuating under the influence of quantum mechanics, which means that it must be a very small foam so that quantum mechanics could have its effect. And what they talk about is that you have this fluctuating space-time quantum foam which would lead to the possibility that universes could quantum tunnel out of the foam.
Pop into existence.
So yeah, they appeal to virtual particle production as an analogy for this budding universes. What they're talking about is some kind of space-time envelope budding off of the space-time foam, rapidly expanding to make a universe. So this quantum space-time foam would be spontaneously producing an infinite number of universe buds, some of which would produce expanding universes that would be similar to our own.
Now, is this foam a necessary component of an inflationary model?
No, not at all. I mean, it's pure speculation that we would have this quantum space-time foam. Now, the people who appeal to the foam do admit that not all the buds that you produce would make, quote, universes. A lot of them would return to the space-time foam. And let me just outline the analogy here. In quantum mechanics, we can actually prove that virtual particle production takes place. In other words, the fluctuations in the space-time fabric occasionally will produce a virtual particle pair. And so this
You
would...
might want to explain what that is.
Okay, well,
We're
it's
probably
not-
getting in deeper.
Well,
than we
it just
want
is
to.
you create, for every particle there's an antiparticle, and if you've got enough energy, you can create for a time being a particle and its antiparticle,
Right,
but
right.
on the condition that they recombine and destroy before you could physically measure them.
Yeah, quantum mechanics demands that this pair of particles that you create
Bring
out of
into
the
existence,
space-time quantum fluctuations, antiparticle and a particle, must return to the space-time foam before there's any possibility of an observer detecting them. That's why we call them virtual particles. Because the uncertainty principle of quantum mechanics demands that they must return to the space-time foam before the observer can capture it in some way.
But you're saying that none of those things, those speculations, are a necessary part of an inflationary model. I mean, we believe that the inflationary model that's been proposed is a pretty good explanation for what we observe to have taken place in the Big Bang and what follows the Big Bang.
Maybe in 5 years we can prove that it is an inflationary hot Big Bang. We're seeing increasing evidence that suggests that.
But these things aren't necessary as a part of that model.
Well, the standard inflationary hot Big Bang model predicts a universe, one universe,
Right.
not many universes.
Okay.
To have it produce many universes, you must speculate that there's something radical that happens to the laws of physics when the universe is extremely young. So if the laws of physics don't change, and Jeremiah makes a comment in chapter 33:25 about the fixed laws that rule the universe. If those fixed laws apply all the way back to the creation event itself, then that means your cosmic models must obey the same physics that we see today.
Okay.
The multiverse models are founded on the principle that that may not be correct, that the laws of physics would remain fixed back to, say, 10 to the minus 34 seconds, and previous to that, 10 to the minus 34, 10 to the minus 43 are the most popular places where physicists want to invoke radically different physics.
Different physics going on. Okay.
Now, let me explain why that must be the case. The virtual particle production analogy, which is foundational to all multiverse models, quantum mechanics demands that the greater the mass of the virtual particles, the faster it must return to the space-time fluctuations. And the case of virtual particle production that we know goes on, the return time is much faster than a trillionth of a second. Now, the greater the mass, the faster
more
the return
quickly
time.
that returns.
Now, if we're talking the mass that we can see in the universe, the observable universe, the return time is briefer than 10 to the minus 120 seconds. So we're going to appeal to the physics that we observe today as being in effect since the creation event that tells us that the multiverse model is impossible.
Okay.
The universe has been here a lot longer than 10 to the minus 120 seconds.
New physics, that's what they're appealing
They're
to.
appealing to, well, in that sense, they're appealing to metaphysics. Your father's comment that they're getting closer and closer to the biblical creation model is accurate, and that now they're appealing to something beyond matter, energy, and space and time and the physics we can
Transcendent
measure.
beginning.
Well, I mean, I have heard too. It's maybe a different way of casing the same argument, but that our observable universe is just simply part of a bigger universe.
Right.
Again, you're moving from our universe to something larger than that, which again is some sort of supernatural, whether it's just another bigger universe or
Well,
not.
it's
But
quantum
there are-
mechanics going the other way. What you're really saying is our present universe is some kind of quantum fluctuation that's part of a bigger universe. But now you have to violate the laws of quantum mechanics and gravity in order to explain the universe in that context. So it's metaphysics again.
Right.
Kind of leads us to this other response here, which
Well,
is that
before
there
we
is
get to that, Dave, I think it's really critical we find a way to rebut this. This is such a common explanation today
okay.
that I think it's critical that we provide. It's not just that you're needing new physics. Even if you were to concede, well, okay, this is metaphysical, it's theological, and I think that point's critical. This is not a scientific rebuttal. It's a metaphysical or a philosophical or a theological rebuttal, which means we should be taking this debate outside of the physics department and putting it in the religion department, because this is religion. You're appealing to something beyond the physics that we see and understand. But let's just, for the sake of argument, concede that these multiverse theoreticians are right. Where does that lead you? I would argue that you're still, in some respects, committing a fatal philosophical fallacy in appealing to the multiverse as an explanation for why we're here. And that would be demonstrated by pointing out that this is simply an appeal to a form of the gambler's fallacy.
Something you can never observe.
Well, let me give you an example of what I mean by this. I brought a coin here with me, and I'm going to flip this coin in front of both of you, and it came up heads. What if I were to flip this coin 100,000 consecutive times, and it came up heads all 100,000 times? My guess is that neither one of you would be willing to bet tails on the next flip.
No, certainly not.
Even if I gave you 10 to 1 odds, you wouldn't bet tails. So, but the one who's appealing to the multiverse as an explanation for the universe really is saying, okay, I've seen 100,000 consecutive heads, but I'm still going to bet that it's tails on the next flip.
I've seen the fine-tuning.
I've seen the fine-tuning.
But I'm going to bet that somehow it isn't really that.
Exactly. Now,
and I'm going to appeal to something that I can never observe outside of my present universe to explain it.
Well, back in the context of this coin, what you're really doing is saying, well, I've seen 100,000 consecutive heads, but it's possible that this coin has not been purposed to come up heads every time. Why? Because I can speculate that outside of this studio, there may exist a lot more coins. What if there exists 2 to the 100,000 coins? Now, for the sake of lay people, that's 2 times 2 times 2 times 2, multiplied 100,000 times, an enormous number. 2 to the 100,000 coins being flipped by 2 to the 100,000 people. And they're all being flipped 100,000 consecutive times each. The individual committing the gambler's fallacy would say, well, if you got that many coins being flipped that many times by that many people, the laws of probability tell us that one of them should produce 100,000 consecutive heads, even if all the coins, none of the
fair.
coins, yeah, they're all fair.
And you just happen to be that person.
You just happen to be that lucky person. Now, we call it the gambler's fallacy because that individual rationalizing along those lines has no evidence that many coins exist. No tangible evidence. Has no tangible evidence that that many people are flipping them, or that they're being flipped 100,000 consecutive times each. And what he especially lacks is any tangible evidence that they would produce different results. And therefore, a rational person would argue, I'm not going to bet tails where I see 100,000 consecutive heads. Now, I've run into physicists and others who have said, well, I realize it's a long shot, but I'm still going to bet tails, because if I bet heads, that means we're talking about a God who's going to hold me responsible for my actions. And I don't want to have this God in control of my life. And therefore, I'm going to bet tails, and unless I see overwhelming evidence the other way, I'm not going to go in that direction. Now, I would argue with that physicist, and I had this opportunity at the University of Washington just days ago when I was up there. I was saying, well, if you're in that position where you're going to bet on this extreme long shot, wouldn't it be a good idea to say, before I bet tails, can I look at the coin? And if you look at the coin and see there's heads on both sides, you'd say, no thanks, I'm not going to bet tails. I can tell that this coin has been purposed to come up heads all the time. We can do that with the universe. We can do the equivalent of examining the coin in more detail. And how we do that is we say, well, the next 6 months, we're going to have the capacity to measure the universe in more detail than we have today. And if in the next 6 months we see that the evidence for fine-tuning and design gets greater rather than smaller, that's equivalent to looking at the other side of the coin and saying, wow, there's heads on both sides. there's no way this is attributed to some kind of natural multiverse hypothesis. This is pointing to the supernatural.
It's not a fair claim.
It's not a fair. The universe has been purposed to come up with the conditions
that it has,
and we can put this to the test.
Well, I would, just as we're getting close here, I would point out, this is by far the most common response, it seems. There are other responses that we may or may not touch on later, but, maybe it's just an illusion, that it really isn't there, or maybe there's some other physics that drives us that, or that God, there's a response number 2, that maybe it's just an illusion, or that God doesn't exist as another response, so that there's a fifth law, or some more physics that we just don't know.
Maybe we should talk about this. Is such an important subject. Maybe we should talk some more about it.
There are at least 4 other responses to this that are worthy of attention, but the multiverse one, at least right now, is the most popular.
Common.
And that's why we spent some time helping people understand it. But next time we get together, we're going to look at the remaining. And by the way, it's a short list. We're only talking 5 responses, only 5 that are possible to come up with. So by the time we're done, we're going to have a complete response to all possible philosophical objections. So join us next time for more reasons to believe in Christ as Creator, Lord, and Savior. Welcome to Reasons to Believe, the television program where we look at new reasons to believe in Jesus Christ as Creator, Lord, and Savior, and for the accuracy and reliability of the words of the Bible. And these last several episodes, we've been examining what physicists and astronomers call the anthropic principle. How when we look at the universe, when we examine the physics of the universe, we see that it's all highly fine-tuned to make life possible, and human life in particular. And we've done, I think, 9 episodes where we've examined specifically these design features and how much fine-tuning we see in each of these features. And in our last episode, we were talking about, this points so obviously to the God of the Bible. How do non-theists, how do deists respond to this overwhelming evidence for design that points to a supernatural creator? And the one we focused some time on was the most popular rebuttal, which is that it's not a universe, but it's a multiverse, where there's an infinite number of universes, all with different physical characteristics. That by pure chance would explain our universe that has these amazing fine-tuned characteristics. And for those of you that missed that episode, we do have all of our Reasons to Believe television programs archived at our reasons.org website. So if you missed the last 9 shows, you can catch them by going to reasons.org. But we'll just pick up kind of where we left off before. And philosophically, there's only 4 classes of rebuttals to the God of the Bible as the causal agent behind all this design we see in the universe and the solar system. Multiverse is one of them. Why don't we just quickly kind of run down what the other 3 are, and then we'll look at each one of those 3 in some detail. You kind of gave us a running summary of that before, Jeff, so why don't you kind of take us through that, and then we'll jump right into it.
Okay, so you've got the idea that there are just multiple universes and we happen to live in the one special case. Then the other is just that it's all an illusion. We really aren't in a fine-tuned universe or anything. That we see it the way it is because we're here, but there's nothing.
We wouldn't be here unless it had the characteristics it did,
Then you also have the idea that while it may appear fine-tuned or something, it's really because we don't have all of the physics in hand. And so we'll, as we continue to look, we'll eventually hopefully discover this 4th law or the next law of physics that kind of ties it all together and makes it appear.
Some law of physics that would explain why we would have all this design
just
there.
Predetermines all of these parameters.
Self-organizing principles, things like that,
Exactly.
Yeah. And then you got, it could definitely be a God, but it won't be the God of the Bible because there's just too much empty space. I mean, we occupy this little part of the universe, and there's a whole bunch of extra empty stuff out there that's really kind of useless as far as life is concerned. And so that it can't be the God of the Bible because he wouldn't work that way.
God of the Bible wouldn't waste his miraculous powers, so the fact that we see 100 billion trillion stars, they would argue means that it can't be the God of the Bible.
I find it kind of interesting that the people who don't believe and certainly don't know the God of the Bible are willing to predict what that God would do or not do.
Right.
That's quite remarkable.
It really is. Well, let's see if we can expose some of that, Dave and Jeff, by going through these. Not the first one, because we did cover that in our previous episode. But let's pick it up with this. And this was actually the first rebuttal. I remember back in the early 80s, when the anthropic principle was really developing some force. And you got people like Paul Davies saying, when we look at the universe, what we see there is overwhelming evidence that it's designed. And that's where this second rebuttal came about. They said, well, of course it looks the way it does. You wouldn't be here unless it had those characteristics. So that was the first of the rebuttals to the God of the Bible as the answer
called,
for the
in fact,
design.
the weak anthropic principle, if I'm not mistaken.
Right. That's one of the explanations for why the universe would have the appearance it is. And, we mentioned in the last episode that all four of these rebuttals that we're going to be addressing are philosophical in nature, even though the scientists pretend they're scientific rebuttals. They really are philosophical rebuttals. And this particular one, I think that's borne out by the fact that it was a philosopher that exposed the fallacy behind the appeal to, well, of course it looks the way it is. We wouldn't be here unless it had those characteristics. So the credit goes to Richard Swinburne. He's a British philosopher. And in the late 1980s, he developed an argument that many other philosophers have copied since him. In fact, I've copied it in my book, but I gave credit to Richard Swinburne for coming up with it. And what he did is he came up with an analogy. He says, in order for all of us to be able to see the fallacy behind this rebuttal, let's consider a firing squad situation. You made allusions to that briefly last time, Jeff. And what you do is you would take, say, a volunteer out of an audience. He did this in front of an audience. And he encouraged a volunteer to come up on the podium with him. And he says, okay, now what we're going to do is go throughout this large audience and select out from the audience the 10 best sharpshooters in the audience. And then we're going to place these 10 best sharpshooters 15 feet away from this volunteer. And then we're going to give these 10 sharpshooters high-powered rifles with telescopic sights, and then we're going to instruct each one of them to aim their rifle at this individual's heart and pull the trigger. Well, that happens. These 10 sharpshooters all pull their triggers. We hear these loud bangs, but the individual on the stage survives the event. And what the individual says to the entire audience, well, of course, I wouldn't be here to talk to you unless they all missed. Now, Richard Swinburne makes the conclusion that that's not what would be most amazing for in the context of that survivor. Someone surviving that kind of firing squad experience, what's going to come to them is, why did they miss? Not that they missed. Well, of course, she wouldn't be there unless they'd all missed. But the whole point is, why did they miss? Because given the circumstances, the only reasonable explanation for all of them missing is that they purpose not to kill her. And therefore, she would be drawing the conclusion, these sharpshooters must have purposed in their heart that I would survive the event. Therefore,
Or
there's
someone
purpose.
else had planned and put blanks in the guns.
Right.
But it was somebody planning it.
Some intelligent being had a purpose for that person surviving. And then likewise, Richard Swinburne says, when we look at all these design characteristics of the universe and the solar system, it drives us to the conclusion that some intelligent entity beyond the universe must have purposed that we human beings would be able to survive at this moment in cosmic history. It's irrational to conclude that we're an accident, just as it would be irrational to conclude that these 10 sharpshooters all accidentally missed. Given their skills and where they were and the kind of equipment they had, the only explanation for them missing is that they purposed that the individual would survive.
Someone planned it. Yeah.
Right.
When you said this one's kind of largely gone out of, it's not a well used argument, or not a popularly used argument.
Very
I guess.
popular in the early and mid 80s. By the time you get into the 90s, so many philosophers were bashing scientists with this one that the scientists gave up on it and says, okay, we concede this is a bad argument. And so today, at the beginning of the 21st century, I don't know of any scientist who uses this as a rebuttal. Now, I guess I've seen one.
Well, as I said, I know people at my former job there at the Jet Propulsion Laboratory who seem to be quite enamored with this argument and will argue tooth and nail that it's still a legitimate argument.
But I would argue that they're probably not that well exposed to people like Richard Swinburne or Bill Craig or J.P.
Right.
Moreland and other famous philosophers who've been active in publicizing this. So at least scientists who are a little bit in tune with what's going on in other spheres of discipline recognize that this has such an obvious fallacy in it. This is not a good argument to use. Of the four we're discussing, at least it's my experience, Dave, this is the least popular of the four today, even though at one point, 20 years ago, it was the most popular. So it's gone from the most popular to the least popular, thanks to the philosophers out there.
Yeah, thank you.
We need the philosophers out there to help us do the job.
That's right.
Well, and as you said, I mean, almost all of these arguments are based in or a philosophical argument, not necessarily a scientific argument. So,
in that sense, it's important that the scientists have enough exposure to philosophy that they realize which arguments are bankrupt and
which
ones
have
are
some
valid.
merit, yeah.
right.
Okay, what's the third one on our list?
That God doesn't exist, or well, basically, it can't be a God, and so as a result, there must be some other law of physics that we're missing that is the explanation that ties all this together.
So
It's basically an argument of ignorance. It's saying that, well, we just don't know what it is yet, but we believe confidently that there will be an explanation not requiring a transcendent agency or God.
well, probably the most popular promoter of this concept would be the Santa Fe Institute, and particularly the founder of the Santa Fe Institute, Stuart Kaufman. In fact, I've got his latest book here. Yeah, here it is, called Investigations. And this is the book where he and the Santa Fe scholars really promote that there's a missing law of thermodynamics that we have yet to discover. He calls it the fourth law of thermodynamics.
These are these self-organizing principles that
Yeah, he claims that there's this fourth law of thermodynamics that would self-organize systems. It begs the question, how come nobody has seen this fourth law? How come we can't measure it or detect it? And why does it violate the second law of thermodynamics? The book starts off with a discussion of the second law of thermodynamics, which tells us that systems tend from order to disorder, and the energy becomes less and less useful to do productive work.
we have seen the law. All of the unexplained design in the universe is evidence for that law. Isn't that right?
Well, that's right.
Well, I mean, it does seem there is a point to that there have been a number. I mean, you know, if you'd have said there is a distinction, but you know, I mean, you could have said, well, why haven't we found the expansion, or you know, this space energy density, which is one of the most dominant factors in the universe, and it's because we weren't capable of detecting it or actually making the measurement or something. So there is a precedence, I guess, for saying that there's something we can't explain, that there's going to be something out there that will explain it and organize it. But this seems to be more motivated by philosophical reasoning than so much we really do expect to find another law.
Well, it'd be fair to Stuart Kaufman when he argues, he recognizes that this fourth law he's proposing contradicts the second law, which is the basis of all science. In fact, a rule of thumb in science, if something violates the second law, then we ignore it because we know it can't be right.
Something must be incorrect.
And he's actually proposing an anti-second law of thermodynamics. But the way he phrases it in terms of why we haven't found it yet, he says, well, in systems that are not overly complex, then what we see is a second law of thermodynamics, that they tend towards decay and disorder. But if the complexity level reaches a threshold, then we see the opposite law, a law of self-organization, where things become more and more advanced and complex. And he tries to argue in the book that we simply haven't done measurements in systems complex enough to detect this. And he actually tries to exploit biology, where he says if we look at the history of life over the past 3.8 billion years, he says there we got proof that there's a fourth law of thermodynamics. Because with life we see that it does get more and more advanced as time goes by. He says that's the fourth law. We simply have to find that fourth law in the universe. We haven't found that yet, but he's convinced we will. But there again, he's looking at life being progressively more advanced, starting with the basic presumption we all know there is no God. And if there is no God, then there's got to be some hidden law of physics we haven't discovered yet. So in that sense, I would argue that he is making a rational point. If you take his assumption that there is no God, then what he argues for is basically the way you got to go.
That's
right.
the way you have to go. Yeah.
Right.
Well, I guess in another sense, we were talking about how by appealing to an infinite number of universes, you're saying there's something outside this universe that governs that. That's how one way that the naturalistic model is actually moving towards a supernatural creation model. And in essence, by saying there's this fourth law that governs things and works outside of the laws we discover,
That's metaphysics.
in
too.
some way you're moving again towards where your naturalistic model looks much more like a creation model, where we would say God is that fourth organizing principle that is increasing the complexity, not just natural processes themselves.
Well, this book and their premises has been really picked up by the Origin of Life community, because in Origin of Life research, they're running into this severe problem that they can't explain life by the physics that we can see. And therefore, they're latching onto the same thing, that maybe there's a fourth law that explains the origin of life. And they make such comments, well, life is intrinsic to the earth, or life is built into the physics of the universe. It's kind of like this strong anthropic principle that the universe must produce life and must somehow advance it. But I'm wondering if there aren't some ways to put this to the test, some scientific ways to put it to the test. Because I think ultimately what the Santa Fe Institute scholars are saying is that once you get to highly complex systems, the more highly complex they are, the more likely we are to see
this law is coming into evidence.
This fourth law. Well, I would argue that we human beings have made some very complex instruments and machines and computers. Do we see any evidence? I mean, Dave, you worked on the Hypercube at the Jet Propulsion Laboratory, probably one of the more complex computer systems ever put together. I would think that one way you could test Stuart Kauffman's hypothesis is to say, well, do we see any evidence of that in these supercomputer research projects?
It's probably not so much the computers themselves that are complex, but it's the potential that they offer for writing computer programs. I mean, just this whole idea of artificial intelligence is the notion of being able to put into the programs of the computers sufficient complexity to where they begin to manifest what we would call intelligence.
Where they,
so I think
software would write software?
Well, ultimately that's what would happen, but that somehow the software ultimately would bring about self-consciousness and the kinds of things that we see within human beings. And of course, one of the axioms that seem to be always the case in the developing artificial intelligence community is that whenever they've been able to make a step and implement some characteristic that they said, if we could do this, it would be some form or some beginning form of artificial intelligence, that when they've been able to do that, then they are able to look at that, what they've done, and say, well, this isn't artificial intelligence. It's just this, or it's just that. All we've done is, like these programs that do chess, for instance, now they have chess programs that are able to beat the best chess players.
Right.
But when you go and look at those programs, you say, well, all they are is searching trees, and they're not really doing the kinds of things that we think is going on within the mind of these chess masters.
Right.
And that just seems to be always the case. Whenever they make us a further step in implementing artificial intelligence, they are always able to look back and say, well, this isn't it yet. We haven't, all we've done is just some programming. We haven't really created artificial intelligence.
Well, I guess the thing I'd like to explore, Dave, is that in pursuing these complex software packages and complex instruments, do we find that they're getting easier to push forward the boundaries of complexity as we move on, or is it the other way around, that we're actually pouring more and more human
effort into it.
and brain power into making the next small step. I mean, if that's the case, that would testify that this is governed by the second law rather than by some undiscovered fourth law. A fourth law should manifest the fact that this kind of research and effort should get easier once we get into the higher levels of complexity.
I would say it's probably harder and harder, and I think that's why they look back and they say, hey, all we've done is we've just put into it some of our own reasoning power, but it's not really intelligence where it's able to learn. Now, I think the area where they're using neural networks has the opportunity for, or opens the gate for the possibility of learning and growing and advancing in sort of an automatic way. And so far they haven't been successful yet in making an artificial intelligence, but I think that's perhaps an avenue that might be able to do the kind of thing you're talking about.
Well, I'm thinking of an experiment where you would, say, develop a computer program. And as that computer program becomes more and more complex with more lines of code, more nested subroutines built into it, we should be able to measure the stability of that software in terms of little errors that creep in or error propagation. And everything I've seen so far is that the program becomes more and more unstable the more complex it becomes. Whereas according to the Santa Fe Institute, you would expect it to go the other way around. So far, those kinds of experiments...
We haven't reached that point yet. We haven't gotten over that
well,
hurdle
that's what
yet.
they keep saying, but I would argue we've gotten to rather high levels, high enough levels that when you compare it to the universe, we would argue that we've done experiments at the realm of complexity they need to make their model work. And it's not just hardware, I mean software, we've done it with hardware too. I mean, what happens even with things like automobiles? The ones that are extremely complex and are highly fine-tuned are the ones you're always taking into the shop.
Right.
So things
true.
keep going wrong, whereas there's an advantage to building a simple automobile engine because it'll be more reliable.
Or an airplane, for instance.
Right,
It's
or a
enormous
spacecraft.
complexity, or spacecraft.
So
It's very difficult to make one that lasts a long time.
if something's got 60,000 moving parts in it, the reliability of that instrument is going to be less than one that's got 5 moving parts. So in that sense, I think we can actually say that by pure science alone, we can put this to the test. But as you pointed out, Jeff, we need to make the point right at the beginning. This is philosophy because you're appealing to something that no one has ever been able to discover or measure.
This fourth one, that God wouldn't, the God of the Bible, if He's the designer, He wouldn't waste so much space and time and effort and energy and so on. He'd just make a few stars out there and sort of a limited number of things that are required to provide an environment for us to live in. How do you respond to that?
Well, it's a popular one. It's very popular for lay people because of who's been promoting it. Namely Carl Sagan and Stephen Hawking. I mean, these are kind of icons, in the icons of science in the lay public's mind.
And it helps that they made the movie Contact and put that in there at least 3 or 4 times too. So
Right. So Sagan's novel and his widely seen movie promote this idea. As a Christian, I'm somewhat encouraged that Hawking and Sagan knew enough about the Bible to figure out some of the characteristics of the God of the Bible. Because the basis of their argument is that when you read the Bible, it reveals a God that doesn't waste miracles. It's a God that performs as few miracles as possible to achieve His purpose. And in one sense, this whole theme that we've been developing on the anthropic principle, the evidence for design, the Christian worldview perspective is that when scientists do their work, when they study the record of nature, they're primarily going to be investigating natural phenomena with natural causes. The Christian worldview would say that should be the norm, but there will be exceptions to that norm. And it's based on this idea that God doesn't waste miracles. But the whole point is it really accurate to say that it's a waste of God's miraculous power to make a universe that's 13.7 billion years old, To make a universe where out to the observable limits we see 10 billion trillion stars. What Sagan and Hawking were arguing, it's God of the Bible, he's not going to mess around. He's going to make one star, one planet, a moon, all the things that we said were necessary. Like Jupiter being in the right place and so forth. But basically all you would need is what we see in the solar system. And that everything else would be a pure waste of effort. There's no purpose in it.
Yeah, but I guess some of that kind of, it always seemed to me this argument somewhat begs the question of what's the purpose, though? I mean, you're presuming to know God's doing this particular thing, and so if that's true, then this is a waste of space. And in reality, we don't know what a lot of that is for, and actually we're finding a lot of that is necessary for us being here today as well. And so, it seems it's an argument born of not understanding what's really going on.
There's a presumptuousness
there.
Well, even pride. I mean, what Hawking and Sagan are saying is that they know as much as God does. They know and understand everything. And I would be a little bit hesitant to say, well, I know enough about the universe to say I understand everything that could be attributed to purpose. But I think the great irony is what you pointed out. Even before Hawking and Sagan made these comments, physicists already knew why we had to live in a universe that was as big and as old as it is. Only a universe that contains 10 billion trillion stars out to the observable limits would be able to produce a star like the Sun, a planet like the Earth, a planet like Jupiter.
Given the laws of physics, the way they've made,
Well, we started off this series talking about the mass density of the universe must be fine-tuned. You make the mass of the universe slightly larger, then all you get is black holes and neutron stars. If you make it slightly smaller, you don't get any stars or planets at all. And therefore the universe must take on a particular mass to get one planet
that has
would
the
have
right
the capacity
characteristics
to support life.
The final thing, of course, is that the right answer is that there is a God who has a purpose and has created all of this. And I suppose in our final program, this is what we're going to spend some time
It's what we're going to do. But given that we've knocked out the 4 possible rebuttals to the God of the Bible, that leaves you with the God of the Bible. So what we've done in these 10 episodes is to show you some positive evidences for why it must be the God of the Bible and why the negative evidences simply won't fly philosophically. Join us next time where we really try to outline the identification of the God of the Bible. Welcome to Reasons to Believe, the television program where we look at new reasons, new evidences to believe in Jesus Christ as Creator, Lord, and Savior, and for the accuracy and reliability of the words of the Bible. And for the past 10, 11 episodes, guys, we've been looking at what's been called the anthropic principle. What we astronomers note in looking at the universe and seeing that it has these exquisitely fine-tuned characteristics that reveal that there's this overwhelming evidence for design at such a high level, it points us towards the God of the Bible. The last episode we looked at possible philosophical rebuttals to the conclusion it's the God of the Bible, and I discovered that each one of those leads you to absurdities or impossibilities about the universe. And we'd like to kind of focus on this episode on what can we learn about the specific characteristics and personal features of the Creator of the universe. Why can we narrow it in on the God of the Bible as opposed to, say, the gods of the other faiths and religions of the world? And I think one place we can begin is the fact that this whole argument for design of the universe is founded on the principle that there is a transcendent causal agent. That I think what opens the door for the whole idea that this fine-tuning does point to a supernatural creator, as we already know, based on the Big Bang and the theory of general relativity, in particular the space-time theorems of general relativity, that the causal agent for the universe must be a transcendent entity.
Someone outside of the universe that exists.
Specifically someone outside of matter, energy, space and time. And ultimately this is based on what are called the space-time theorems of general relativity. Stephen Hawking and Roger Penrose in 1970 published the first of these space-time theorems, which basically states that if the universe contains mass, and of course we don't doubt that it contains mass, we're all living proof that it contains mass. Some of us have more mass than others, so
Hey, what's going on here?
what's going on here, right? But the second condition is that the universe is governed by the equations of general relativity. And when Hawking and Penrose made this proposal in 1970, we were fairly confident that that wasn't a true assumption. But today we're extremely confident that it's a correct assumption. Penrose himself has been on record as saying the theory of general relativity is the most exhaustively tested principle in all of physics, and it's the best proven principle in all of physics. Especially in the last 24 months, there have been a number of new tests of the theory of general relativity which simply add to the weight of proof that this is the best proven principle in physics.
Really should be called the law of relativity rather than the theory of general
Well,
relativity.
it's better established, for example, than Newton's laws of motion, or the
yeah.
laws of gravity. So both conditions of the space-time theorems are now beyond doubt. And what these space-time theorems tell us is that there's a coincident beginning of all the matter in the universe, all the energy in the universe, and all the space-time dimensions associated with that matter and energy. But I think what's often missed by our peers in astronomy and physics is that there's a corollary to these theorems which state that there is a causal agent that brings matter, energy, space, and time into existence, independent of matter, energy, space, and time. So by definition, that means the causal agent for the universe must be some transcendent entity, some entity capable of cause and effect actions and creation outside of matter, energy, space, and time.
So now we want to ask the question, looking at this universe that's showing this design, what can we learn about the nature of this agent or this entity, this transcendent?
Well, before we go to the second step, I just wanted to alert everybody that kind of the icing on the cake is this paper that just got published. It's the latest of the space-time theorems of general relativity, produced by three famous theoretical physicists, Alexander Vilenkin, Alan Guth, who invented the inflationary Big Bang model, and Arvind Borde. And what a number of theoretical physicists have done over the past 3 years is to produce a whole set of space-time theorems of general relativity which take this proof beyond just classical general relativity and generalize it to all the quantum gravity cosmic models, all the inflationary Big Bang cosmic models, in fact any cosmic model of the universe where we have a second law of thermodynamics. So I think in a much more general matter, we're driven to the conclusion that the causal agent of the universe is a transcendent entity.
So since,
Actually, I was going to say, I think you made the comment that you think, or it seems that some of the astronomers and folks missed that. I would actually almost say they realize the implication of it, and that's why this idea of an infinite, these multiverses and stuff was so popular as well. As not only did it solve the anthropic principle,
Right.
but it also got rid of the transcendent creation event too.
Right.
It seems that it was almost more motivated by the response to get rid of the transcendent creation event, and that you can explain the anthropic principle with it as well.
But I find it comforting that these space-time theorems, as we learn more about the universe and the physics of the universe, those proofs are becoming more strongly established rather than less strongly established.
So what you're kind of saying here is that while we recognize that general relativity as a theory does break down in the quantum realm. I mean, we can't go back to the very beginning
Classical
event.
general relativity would.
That they're able to prove these theorems in the context of a general relativity that includes the quantum theory.
Right.
Is this done in the context of kind of a string theory?
Some of them are. I mean,
Yeah.
in fact, you'll find the references to all this in this book, The Crater and the Cosmos, that I updated recently. There's a chapter there where I review all the space-time theorems that have been developed since the one in 1970. And so you can see over the course of the past few years how these theorems have become progressively more and more powerful. in their capacity to explain why the physics is the way it is.
Okay, and so they've reinforced the idea of a transcendent agent.
And I would predict that evidence is going to get even stronger in the years
Right.
ahead, rather than weaker. But of course, we can learn a lot more than just the transcendence. I think that's where you wanted to take us, Dave. That
Right. What are some of the additional things that we can derive from this finely tuned universe that we see here about the nature of that designer?
Well, an astronomer that volunteers for us at Reasons to Believe is Bill Keel at the University of Alabama. And over the course of the past 15 years, he's been developing a new concept of the anthropic principle. Not just that the universe is designed to provide us with a suitable place in which we can live, but that the universe is also designed to provide us with a special viewing window on the heavens. That our location in the universe is not only ideal for our existence, it's ideal for our capacity as human beings to actually observe the universe. It looks like that there must be a being that wants us to see the universe and to see the design that he put in the universe for our benefit, a God that wants to be discovered. And how Bill Keel developed this, he and his research team, is to kind of look at our spiral galaxy and say, well, where do we find most of the stars in our galaxy? Well, almost all of them, 99.9% plus, are found in one of three locations. The central bulge of the galaxy, one of the globular clusters, or the spiral arms. And our star, the Sun, is in neither of those locations. And the problem with those locations, as Bill Keel has pointed out, the bulge of our galaxy, where about half the stars of our galaxy are located, the star density is very high. So high that nearby stars would disrupt the orbit of a planet like the Earth. And then there's radiation there that's not nice for life. I mean, there's a black hole there you want to not get too close to. So there's radiation there, and there's gas and dust that would block your view. And if you were located in the central bulge and looked out at the night sky, what would you see? You'd see a whole bunch of stars very close to you that would illuminate the night sky, and you really wouldn't see much beyond the bulge.
That's given that you could live there.
Even if you could live there, as an observer, you wouldn't see much because of the density of stars. Same thing would be true if you were in a globular cluster.
All you'd see is a bunch of stars around you.
I mean, we should show people what a globular cluster is. I don't think we have a visual, but a globular cluster, you've got a 10 light year diameter volume with 100,000 to 1 million stars packed into those 10 light years. And
Kind of like a bee cluster here.
Right.
If you were in the middle of this bee cluster, you wouldn't be able to see out. All you'd see is other bees.
Right.
Well, and for scale too, I mean, that's 10 light years, and you have, what do you say, 100,000?
100,000 to 1 million stars.
If you take take a 10 light year, 5 light years on either side of us, you get about 4 stars in that area.
Right.
I mean,
Right.
we have virtually nothing in there. So.
Instead of 100,000 stars, we only get 4.
4,
And with 100,000 stars within 5 light years of us, looking up at the night sky, you're not going to see anything except those nearby stars. And then in the case of the spiral arms, Bill Keel said the spiral arms are loaded with dust. And the dust is going to block your view.
the view. Yeah.
Never mind the supergiant stars that happen to reside there
Now,
too.
when you call attention to this ideal place, there's also some sense in which if we lived at a different time, wouldn't there be the horizons in terms of being able to see out to the outer outer distances of the universe that would be cut off because they fall behind some kind of velocity of light cone or something?
That's accurate.
Yeah, I think
It's
there's
not just that we're at the right place to see the universe,
right
we're also at the right time.
Okay.
And
If we were a little earlier or a little later, that our view would be hindered. Or
well, the problem of being created earlier in cosmic history is that the universe gets older and older, and hence bigger and bigger. It forms more and more objects. More stars form, more planets form, and in that sense there's more to look at as time goes by assuming you don't have too many stars dying out in the meantime. But as you were to be created later in cosmic history, well, that would be after most of the stars have formed and burnt out. So you wouldn't be able to see as many stars because a lot of them would be dead and invisible. And then the other factor you point out, as the universe gets older and older, it expands faster and faster.
Right.
Once you get past about the first 7 billion years, this space energy density term that we mentioned early in our series
Right.
would take over and expand the universe at an accelerating rate, which means that the most distant objects in the universe will move away from you at greater than the velocity of light,
Right.
therefore become invisible. So I think one of the depressing things we astronomers have to look forward to today, as the universe gets older, as we get older, there's going to be less for us to look at because the most distant objects move away from us at progressively more and more rapid velocities.
So
To be fair, though, that's going to happen in about 2 trillion years. I mean, it's a fair ways off.
It's a fair ways off, and it's not something that concerns me about my immediate career in astronomy. So,
But there is some sense in which being at this right time gives us the biggest view and the biggest opportunity for studying.
13.7 billion years after the creation event is when you get the most to look at
Right.
in terms of the physical universe.
And what does this tell us about? Is there anything we can derive from this alone now?
Well, let me take the location one step further, Dave. Bill Keel kind of laid out the fact that we're at the ideal location in the galaxy, a highly fine-tuned location where, less than 0.001% of the stars would reside. We happen to be at the co-rotation distance. I think we discussed that in one of the earlier episodes. And so this puts us at not only at the ideal location, but in a stable ideal location in which to see everything that's in our galaxy. But I would argue that our galaxy is also at the ideal location. It's no accident that we happen to be in something called the local group. I mean, in your research, you were examining nearby galaxies. Well, the whole point is we can see more than just the nearby galaxies. In terms of where the galaxies reside in the universe, 99.9% reside in these rich clusters of galaxies, where you'd have 10,000 galaxies or more in your cluster, which means if you were an observer in one of the galaxies in that cluster, looking out at the night sky, you'd see this huge swath of light across the night sky being the adjacent galaxy to you. And that nearby galaxy will block your view of other galaxies around you. I mean, in one sense, you look up in the night sky today and you can see the Milky Way. And that Milky Way blocks out the images of galaxies behind that spiral arm of our galaxy. But what if we had 2 or 3 nearby large galaxies that would block out the rest of the sky? And what if there were 10,000 galaxies just behind that? At best, you'd be able to detect that you lived in a cluster of galaxies, but you wouldn't be able to see the rest of the universe. But as it is, God has placed our galaxy in the local group, a group that has only 24 galaxies, of which only 2 are medium size. There are no supergiant galaxies in our cluster. The other 24 are dwarf galaxies, and these 24 galaxies are spread far apart, which means we get a clear window. And then another thing to thank God for is our local group is on the extreme outer fringe of the Virgo supercluster. And so we're not only located in the best spot in our galaxy is in the best spot in the universe. And then I think the question you wanted to ask was?
What does this tell us now about the nature of the designer? Is there something we can derive from that?
Well, I don't want to do all the talking here, guys.
Yeah.
Obviously, I think what it tells you or suggests is that maybe there's a reason why we're at this ideal time and ideal place. Could it be that there's a creator that wants us to discover everything that we can see in the universe?
Well, the scripture, of course, tells us that the heavens are there to declare his glory and show us his handiwork. And I mean, that's anyone who looks up in the night sky, whether he's a scientist or just a person out looking up at the sky, no particular understanding of what it is, yet he's overwhelmed with the beauty of it and the immensity of it. And the more he learns about it, the more evidence it provides for whoever put it into place is an amazing person, amazing entity or agency, if we want to limit our terminology here.
I think too. I mean, you say, okay, if we're in this supercluster of galaxies, I can think of at least two of the most significant recent discoveries in astronomy. We wouldn't be able to study the microwave background radiation. We wouldn't be able to to study the distant supernovae that tells us the universe is now expanding. I mean, I can think of at least two or three major discoveries that we wouldn't be able to have made simply because you can't see that far.
And that are showing even further these design characteristics that imply and declare the glory of this and the handiwork of this agent or this God.
Well, what Jeff said is right on target. I mean, the strongest design evidences we have today for a supernatural creator require us to be able to see the whole of the observable universe. And if we weren't at this location and at this time, we wouldn't be able to come up with that kind of evidence. Therefore, it strongly suggests that God wanted to be discovered. And it's not just that the heavens declare the glory of God. There's all kinds of scripture that points that it declares His righteousness, His power, His love. So there's something in the universe that tells us about the characteristics of God. In order for us to discern that, we got to be able to see it. Well, maybe we can move on.
Well, I was thinking, we got just how God is loving. We look at, I think some fellow by the name of Brandon Carter came up with this idea of the anthropic inequality, that you look at the development of the universe and what it takes. You've got to develop heavy elements through stars and make galaxies and have second and third generation. And it just takes a long time for that to happen. Billions of years. And yet we can also, or for advanced life to be in place. But you can also look and say, okay, how long is it before that window is going to close? And it's measured in thousands of years, tens of thousands, maybe hundreds of thousands of years, but not billions of years. So you've got this long time being built up to where you can have intelligent life, and then it disappears very quickly after that. That it seems that there's this purpose and design that I'll spend a lot of time making sure you can have. I mean, even though we're here for a short period of time, it required a lot of investment.
Well, when you read Brandon Carter's paper, he comes away amazed that human life can be here so quickly. 14 billion years, he says, is remarkable that everything could be put in place that fast, given the laws of physics. In fact, something I wrote in my book, The Genesis Question, you need 4 outstanding miraculous interventions to get human beings here as quickly as these 13.7 billion years. But then Carter goes on to say that the window of time, once you got human beings on the scene, by the same laws and laws of physics and characteristics of the universe, is really narrow. One example I can give, it's come out of the supernova, probably not the neutrino measurements coming out of the sun. These new neutrino measurements that are really just months old tell us that the sun right now is in an extremely stable burning phase, where it's been stable in its luminosity for the past 50,000 years, and it's got another 50,000 years to go. And so there's this narrow window.
So there's a window in which the environment is appropriate for complex life, but that window wasn't open until a certain time, and it'll deteriorate quickly after that time. So here's this 50, maybe 100,000 years where complex life can exist in this environment.
John Barrow and Frank Tipler, in their book, The Cosmological Principle, made the point that when you look at all the characteristics that are necessary to sustain not just human life, but human life with civilization, that the maximum window of time for human civilization is 41,000 years wide.
41,000, amazing.
Our own
Is
research...
that just for our...
No, they said that
or
would apply to any advanced life capable of developing civilization and technology, no matter where it would be in the universe, whatever conditions it might be.
So we're just about out of time here.
Yeah.
Well,
and the fact that it's 41,000 means that would indicate that that's fairly well constrained, that it's plus or minus a few percent, not plus or minus Factor of two, yeah.
Well, they were trying to make it as broad as possible, and that's about as far as they could get it. My own attempts to look at the numbers, I would argue that 20,000 years is more like it rather than 41,000 years. But that is human civilization.
Sure.
And we've had human civilization on planet Earth for 10,000 years.
So we're just about out of time here.
Well, we got 10,000 more
10
to
more.
go.
Oh, well, okay. Another 10,000.
So you don't have to change your investment strategies too much. So,
Now, what would you feel that this characteristic of our universe, the fact that there's only this very narrow window of time, and all of this preparation had to be made in order to bring about that window, and it only lasts a short time, does that tell us anything about the Creator?
well, Carter himself made some interesting, had some interesting insights on this. He says it's a factor of 1,000,000. The window of time for humanity is 1,000,000 times shorter than the amount of time it takes to prepare a place for humanity. And he says to explain that factor of 1,000,000, it seems to indicate there must be a very high value for the human species on the part of the creator of the universe. And an analogy that's been used is to think of a father buying gifts for his children at Christmas time, maybe spending $1,000 on gifts for his kids, knowing that his kids will destroy all the gifts in the first 20 minutes after they open the packages. Well, we all laugh, but maybe not to the degree of $1,000. I'll bet you we've done that with our kids.
Well, maybe a similar one, but maybe more to the point, is how much parents invest in the education of their children, and then how often those kids go to school for 4 years in a college and end up rejecting their parents' values and living a reprobate life, wherein all of that investment has gone into those 4 years.
Right. And what would motivate a father to do that?
Yeah,
I think it speaks to the
It's
fact
love.
that it's love.
it really is love.
Only a very loving being would spend those kinds of resources on something that lasts for such a brief period of time. And therefore, this demonstrates that the creator of the universe is a caring being, a loving being, to a far higher degree than we can even conceive of care and love.
Well, it also would speak to me that there's, this isn't coming so much straight out of nature, but you look at, what God is doing here, that He's conquering sin and evil, that, that He's powerful enough to create the kind of universe that He wants to make that happen. He's not limited, and, He could have made it umpteen million different ways, if not more, but He chose to do it this way, and He has that power to make different laws of physics to do things differently as He chooses. So,
Well, that's something you see in the Bible, is that, we know God can do it differently because the last 2 chapters of the Bible speak about a different kind of universe with different physics, different space-time dimensionality. And therefore, in answer to the question, couldn't God do it differently? He could. And therefore, that leads to the deduction that there's probably more in the physics of the universe than just the fact that it provides a home for us. There's probably more in the physics of the universe than just this anthropic principle inequality. And from my perspective, that's where the greatest evidence for design really lies. I know we're out of time, so I'm going to suggest that we pick this up because it is a very important theme that we human beings always seem to miss the most significant evidences for design. And I think it's because of what you suggested that points out the justice of God and the mercy of God. And that is emotionally difficult for a lot of us to face, that we're looking at a universe that was created not only by an all-powerful creator, but one that is just and merciful and loving as well. We'll pick this up next time. Welcome to Reasons to Believe, the television program where we explore new reasons to believe in Christ as Creator, Lord, and Savior, and for the accuracy and reliability of the words of the Bible. And we've been looking at the scientific evidences for the God of the Bible and His characteristics, part of a series we've been doing on the anthropic principle. How when we astronomers observe the universe, we see that it has the exquisitely fine-tuned characteristics that would allow for the existence of a life in human beings in particular. And we're wrapping up this series by focusing on these fine-tuned features of the universe and asking the question, what can we learn about the Creator by carefully examining these dozens of fine-tuned characteristics that point to some kind of design? What kind of designer is out there? I mean, I think in one context, our peers already recognize that it points to design, but the next question is, who is a designer? And in our last episode, and incidentally, our episodes are archived at our reasons.org website. So if you've missed the 12 episodes that are previous to this on this series, you can go there at your convenience and either listen to the episodes or you can watch them in video. It depends on the bandwidth of your computer.
We also invite comments too.
Well, we'd especially appreciate your comments on this series of shows we've done on the anthropic principle, your criticisms, what we could have done to have made it better, suggestions for future themes that you'd like us to explore on our Reasons to Believe show here. So yes, your suggestions, comments, critiques, very much appreciate hearing from you. And if you could let Jan and Paula Crouch and the folks at TBN know what you think about this show, they'd appreciate hearing your comments as well. So do keep those letters and postcards streaming in. They appreciate it, and so do we. Well, we kind of left off last time by noting that just through the theory of general relativity, we can establish that the designer is a transcendent entity, a being that transcends matter, energy, space, and time. Then the anthropic principle itself, of course, tells us that the Creator must be very intelligent and very knowledgeable. It takes a lot of knowledge and an intelligence and creativity just to be able to fashion all these characteristics of the universe in such a way that would permit our existence. That's evident from everything we've been saying in this series. But we spent some time noting that it's not just that the universe has been exquisitely designed to allow for our existence, it's been exquisitely fashioned to give us this ideal viewing platform. We are created at the best time in cosmic history and at the ideal location. In fact, we discovered that the location is very narrowly fine-tuned. The vast majority of the spaces of the cosmos simply won't give you a clear view of the universe. That's true for all but one place in our galaxy, and we're at the best time. And this tells us that the one who's responsible for creating the universe must have wanted us to discover things about him by looking at the universe. You know, the biblical context, the heavens declare the glory of God. They declare his righteousness. They declare his love. They declare his power. In order for that declaration to be effective, we need to be able to see this universe in which we live.
In fact, you could, I suppose, argue that short of an explicit personal relationship, some of the things that we've just been talking about are the best ways in which a designer could communicate some of these characteristics that we've been talking about here.
Right.
You can't really, unless you have a personal relationship, you can't communicate love directly. But if you think about how would you do it indirectly, it's by showing how much you're willing to invest in that person, which God has shown in his willingness to spend the time and the effort, all of those things that you talked about, in designing and preparing a place for us to live. That communicates a real interest that we would really call love.
Right.
I know as children of a parent, the kind of investment that a parent makes in a child is a reflection of their love for that child.
Well, it was British cosmologists that looked at what we discussed last time, the anthropic principle inequality, how it takes us an enormous period of time to prepare a place for humanity, and yet the window of time in which human civilization could foster is like 1,000,000 times shorter. And how would you explain that other than by invoking a creator that cares for us so much? He's prepared to invest all those resources in something that's going to last a very brief period of time. So care and love, creativity, intelligence, power, intellect, transcendence, all this is coming out of this anthropic principle and its ramifications.
Well, one thing that kind of, I was just we're looking at, okay, you've got various characteristics of the universe. What does that tell you about the creator or the person who put that in place? And one thing I find that I'm going to guess is probably a tendency amongst most people who do this sort of, who work in the sciences, but that I'll sit there and you'll work with things that are really quite phenomenal, but you work with it every day, and so they seem sort of,
You get used to
you
it.
get used to it
Mundane.
almost.
They don't
I mean,
seem to be
mundane,
as-
yeah. And,
Everything's amazing. So
I have to wonder if you have to just kind of step back a second and realize, what you are. Okay, yeah, we are looking at a transcendent beginning. We are looking at this universe where we live in a very optimal place, where we can see to the far reaches of the universe and see just amazing things that.
well, just like you can get used to the fact that your wife loves you, and kind of take that for granted. Likewise, we can take the love of the Creator. I mean, we're so surrounded by it that we just, quote, get used to it and don't pay any attention to it. But there is this need to step back. And I think that's one thing the universe provides for us. There's just a sense of awe when you look at it that it almost forces you to step back. The other thing, Dave...
I used to do that, by the way. You mentioned this. I used to spend quite a bit of time up in the Owens Valley Radio Observatory, sitting in front of a console and controlling the antennas and running the tape recorders and recording data, and then when I would go off of my shift, sometimes it was in the middle of the night, and so then I would go outside and take a walk down the road, and this observatory was way out in the middle of nowhere, so it was just pitch dark, and the sky was just absolutely gorgeous. I mean, it was just incredible, the view that you had. And it would cause that kind of response. You would look up there, and after having spent all of that time just doing technical things, and then to go out there and just to be overwhelmed and awed by the glory of this creation, it really causes a response within our hearts and minds.
Well, Dave, I'm so weird that I had that kind of response when I saw the little wiggles coming out on the on the chart paper.
Yeah,
It's like,
right.
wow, look at this thing. So, but yeah, that's the scientist.
Yeah.
But something else is that this really communicates to everybody. Not everybody's got the Bible, but everybody does have the universe. So anybody can walk out there and look at the heavens and come to the recognition of certain truths about their Creator.
There is this other characteristic too, and that is the fact that men and women do have this almost this hunger, this desire to know whether there is something out there, whether there is purpose, whether there is destiny. And I know that this is something that some people just set aside and say, well, it's all just people's illusions and imagination. But there are others who are not satisfied with that. And
Well, scientists who are not Christians and yet take this seriously try to claim that this is something that evolved to make us a more survivable species, that we human beings simply wouldn't survive very well unless we had the illusion that we had hope, purpose, and destiny. My counter to that is, how come we're the only species that has that? If this is something that evolved into us from the past, then why do we not see even a hint of these drives in other species of life? Now, interestingly, we do see something that at least the animal species all have in common, and that's a desire to press for self-preservation.
survival.
And so it's like any animal species you examine in the realm of biology has built within it this desire to preserve its life or the life of its offspring. And so it's like every species of life is fighting for this longevity of life, which is difficult to explain given that nothing can last forever anyway. But all life seems to have it. And from a biological perspective and a creator's perspective, it's important that all life have that. But where did it come from? And again, I don't know of any biologist who's come up with a non-theistic answer for where this self-preservation subroutine came from. I can't think of an easy way to put that into the genes. Dave, you're old enough, and I'm old enough to remember that classic movie of the 60s, 2001: A Space Odyssey. And maybe you've heard of the book and the
Oh,
movie.
you can get it on DVD now,
Yeah,
so you
that's
can watch
right.
it at home.
But kind of the heart of that storyline is this supercomputer on board the spaceship that has built within it a self-preservation subroutine.
Correct.
And I remember back in the 60s, my professors telling me it would be just a matter of time before we'd be able to write software that would give computers a self-preservation characteristic. Well, I mean, you've been involved in writing computer software for decades, and that hasn't happened.
Hasn't happened yet.
I mean, we don't even know how difficult a problem that would be at this point. We can't even frame the difficulty of that project. And yet all life has it. Where did it get it? Even bacteria have that property built within them. But we human beings are different. We also have that self-preservation subroutine built into us, but we've got these other subroutines, a desire to seek after destiny or purpose, or the
And we're
desire
willing to
pursue hope.
sacrifice ourselves in order to achieve that for our children.
That's right, or even ourselves. Kind of goes by the psychological name of midlife crisis. But when you get old enough, you reach the point, there's got to be more to life
More to
than
life.
just living another couple of decades.
Yeah.
And at some point, you begin to seriously wrestle with the fact, and where am I going to find this destiny or this purpose in my life? And you actually reach the point where you're willing to trade a few years of your life in order to achieve a greater sense of destiny and purpose. Even you young guys sometimes run into that. So, I mean, why do you go into astronomy? I mean, do you go into astronomy to preserve your life or to make a lot of money?
Not likely.
Not likely. So that might explain why there's so many Christians in the field of astronomy. I don't know.
So, fascinating stuff to do, but
But the whole point is, where did these drives come from? If the chimpanzees don't have it, if the Neanderthals didn't have it, no other life form has it, how do we human beings come up with such powerful drives for which we can find no biological link or past history?
usually when there is something like that, I think others have discussed this, some philosophers, that whenever there is some need that we feel within ourselves, it's usually because there is some opportunity to satisfy that need. And in this case, a desire for hope, purpose, and destiny is a reflection of the fact that there is built within us well, as one scientist philosopher put it, a God-shaped vacuum within us
Right.
that is filled only by a relationship with the Creator Himself.
Well, that's an excellent insight, Dave. I mean, why would we possess a desire to seek after destiny and purpose and hope if there was no hope, purpose, or destiny for life?
Why do we have hope for it, right?
I mean, why? I mean, if you're going to blame it on evolution, why would evolution evolve this if it didn't
build
exist?
that into us if there wasn't.
And therefore, it speaks of a creator that actually has a purpose for us and a destiny for us. That's why he placed these desires within us. And we all share it. I mean, no matter what country you go to, no matter what religious system they're raised under, you see that they have those drives.
That desire. That's right.
So that seems to indicate that there must be a creator that has built in ahead of time a purpose for humanity. He himself has a destiny, but he wants to share that destiny with us. So again, it kind of shows us his love, his concern for us, but also his an eternal purpose for us. So in that sense, it kind of speaks of an eternity in the context of God's plans, why He created the universe. Well, probably the last thing we need to address here is that the greatest anthropic principle of all has largely been ignored by the scientific community. I mean, the scientific community is focused on the fact that when we examine the universe, it has these fine-tuned characteristics to provide a home for us. And we've added it also provides a viewing platform for us. But I think the biggest thing they missed of all is it provides us with the right environment to encourage us to depart from evil and to follow virtue. That if you look at each law of physics, each constants of physics, if you look at the way space and time are designed, look at the gross features of the universe, everything has been optimized to provide us with a maximum encouragement or exhortation to depart from evil and wickedness and to pursue virtue and righteousness. Not that we can be virtuous by ourselves, but there's lots of encouragement
Right.
within nature itself that would cause us to go to God and say, hey, I want help to do what I can see.
They're prods,
Yeah.
sort of
And why would those prods be there
sticks in the ribs.
if there's no possibility that we could somehow pursue and achieve virtue
Right.
through God's help?
You might want to.
you want an example?
Yeah, it might be good to have a couple. 'Cause I don't know. First,
Well, let me try to do this quickly.
Well,
but-
let me make one comment along that line. One of the things that we, of course, know from the Bible is that God has laid down certain commandments. There are certain laws. Don't do this, don't do that, do this, do that. But, it isn't that when we violate those commandments that God is somehow sitting up there with a lightning rod ready to zap us when we go outside the boundary of those commandments, but that He has built in to the universe consequences of violating those
Right,
laws.
right.
There are certain limitations that are just built in that when you step over the boundary, something happens. Something goes against you. And now you're going to
Well, I'd argue it's
give a
not
couple
just
of examples.
consequences. There's consequences when you do evil things.
Yes.
But there's benefits when you do
When you do
virtuous
virtuous
things.
things, exactly.
And so it works both ways.
That's right.
And this shows the love of the Creator, but it also shows His justice in trying to guide us into His right path.
Discipline.
Probably the example that all of us could identify with, at least those of us right here, is, I'm the proud father of 2 teenage boys, although my wife points out that we're really the parents of 8 teenage boys, because each one has 3
Several
of their
friends.
friends. So we're always feeding 8 boys over to our house, and one of the things that they love to do is to borrow my tools from our garage, take them out into the backyard or the front yard where these 8 boys have all their high-tech toys and other things that teenage boys love to get into, and they repair and soup up all their little devices. But they have a difficult time remembering to return the tools to the garage. And we have an automatic sprinkler system both in our front yard and our backyard, so when these tools are left outside for several days, they accumulate a lot of rust and corrosion. And so I've been trying to instruct my boys that, when you abuse your tools in that way, the next time you want to use them, they don't work as well for you. And you discover that you experience a little more pain and you have to work a little extra to make those tools effective. And one way I try to drive that lesson home is I pick up all these rusted out tools, I give them some steel wool and say, keep working on the tool until all the rust is gone. Now they experience a lot of work and a lot of pain. But I think that's what physics is trying to do to all of us, is say when you abuse your tools, they're not going to work as well for you.
That's right.
And it's something we see recorded for us in the 3rd chapter of Genesis, that when Adam and Eve rebelled against God's authority, God told them, from now on, you will experience more pain and you will have to do more work. But as we read through the Bible, what we see the Bible teaching is that the amount of extra pain you experience is in proportion to the evil you commit. And the amount of extra work you have to do is in proportion to the evil you commit. And maybe evil is too strong of a term, because I think one thing we've observed as scientists, if you start with a wrong worldview on the record of nature, and you wind up doing experiments that really are not productive. And so I've seen scientists go up these blind alleys and basically they're experiencing the same extra pain and extra work without a lot of productivity because they had the wrong worldview perspective on the universe. So I'm trying to broaden it just beyond this whole concept of evil. And I would argue that this applies sociologically, that if we abuse our kids become less productive in achieving the purposes we want them to fulfill. So we as fathers get stuck with more work and more pain. I mean, if my sons take out the trash and they leave a whole trail of trash between the front door and the backyard because I was yelling and screaming at them to take out the trash, I get stuck with a lot of extra work and more pain.
Probably one of the toughest things as a father is when your kids go off from the path that you hope that they will follow when they get older, and all the grief that you experience, let alone the extra cost that it brings into your life. I think that's the toughest thing for parents, to see their kids.
Well, you know, Dave, in Genesis 3, it talks about how the woman will experience more pain in childbirth
Childbearing.
because of the sin. I don't see that verse so much referring to the physical pain
I
of
agree.
childbirth. I think it's the spiritual
It's the
trauma.
long-term.
Watching your kids go down evil paths
Right.
if you don't want to see them go down.
That's right.
So the father experiences the pain almost to the same degree as the mother does. And likewise, the women do not get off scot-free when it comes to extra work. It's something that's generic to all of humanity.
So what God has done here then is He's built in sort of self-constraints, as you might say, that is constraining evil, protecting men from going too far, but also giving them lessons, bringing discipline into their life, encouraging righteousness and discouraging unrighteousness.
Right. And I would argue these laws of physics also restrain the amount of evil that we can perpetrate in one another. It's not just that as I commit more evil, I experience more pain. There's certain evils I can't commit, even though I want to commit them. And I look at particularly the way God has structured space and time. We live in a universe described by 3 very large dimensions of space that are rapidly expanding away from one another. That has the benefit of keeping us all relatively far apart. So when I want to perform evil deeds on the human race, there's only a limited number of people I can
you
have
can
contact
affect,
with
yeah.
because of how geographically separated we are. And likewise, I think of the way God has structured time. Time is unidimensional. It can't be stopped. It can't be reversed. And that limits, again, how many people I can harm by my evil deeds and words and thoughts. And
The fact that I'm limited in my own personal lifetime
You only
certainly
got-
brings about
Right.
constraint as well.
we don't live forever. So all these are tools that God uses. And why don't we live forever? The physics structures restrains us from how long we can live. So in that sense, we can look across the spectrum of physics and the characteristics of the universe and see not only that God is built in design, but it's an optimal design. It's like everything I look at in terms of the constants of physics, space and time, the way God has designed the earth, the mountains, the seas, the rivers, the deserts. It's like everything has been optimally designed to limit the expression of evil in each one of us, but also to give us the maximal encouragement to pursue a pathway of virtue and depart from a way of evil.
The whole end of this whole thing, though, of course, is that this is a limited universe, a universe that is going to end once He accomplishes the purpose for which it was made.
Right.
This is not a perfect universe in that it's one that we would necessarily want to live in forever, but it's a universe that accomplishes this purpose of overcoming evil and then allowing God to bring those who are willing to be a part of His plan into the next universe, into the next world that He's going to create.
Well, God has also promised to help us with this problem of evil. In fact, the whole message of the Bible is we can't make it unless He does help us. So there's things built into the physics of the universe that encourage us to go to Him. Because we try to be virtuous thanks to all this nudging from the physics, and we discover we can't do it. But we realize there's this very loving Creator out there who is all powerful, and hey, He set this all up for me. Surely He's going to help me with this problem. And as we've been professors, it reaches a point where the students realize, I need to go to the professor and get some help. And that's kind of the moment we're waiting for to help that student along. And likewise, God has structured the universe to encourage us to go to Him for help. I think your point's valid, Dave, that this isn't the end.
This isn't the end.
God is a universe or a creation ahead of us that's very different from this universe, where there will be no sin, because only people who have been helped by God to conquer the sin within their life go there. And it's a place where we're not limited by space and time. We're not limited by the physics. Gravity isn't going to be the problem that it is now, or thermodynamics. Maybe you're not so excited about this, Jeff, since you're so much younger than us, but We won't have to worry about gravity pulling our faces down. We won't have to worry about thermodynamics and electromagnetism causing our skin to deteriorate.
Yeah.
But most of all, we won't have to worry about the fact that space and time restrain our capacity to be intimate with one another. We're going to have the capacity to express love in a way that's impossible in this space-time limited universe. So I think this anthropic principle not only shows us a lot about why God did things the way he does, but what the future is going to hold for all of
Yes.
us. And I think that's the greatest hope of all in the anthropic principle. It shows us that we have a future that's really valuable and fulfilling and rewarding beyond what any one of us can think or imagine. 1 Corinthians 2:9.